Hello and welcome to Sleepy Science. Tonight, we are going to explore a universe filled with hidden structures, forgotten ages, invisible forces, and questions that continue to challenge even our deepest understanding of reality. We will follow experiments where the future seems to leave traces in the past, travel through oceans buried beneath frozen worlds, listen for particles passing silently through your body, and discover how matter, memory, time, and consciousness may be far stranger than they first appear. Across 30 calm and thought-provoking mysteries, we will move from the smallest quantum events to the largest structures in the cosmos, slowly uncovering how much of existence remains unseen, unexplained, and still waiting to be understood. Before we begin, tell me in the comments where you are listening from and what time it is there. And don't forget to like the video and subscribe for more calm, mind-opening science. Now allow the noise of the day to grow quiet. Let your thoughts begin to slow, and let us begin. When the future leaves traces in the past, experiments that challenge cause and effect. There are experiments in which a photon is already inside the machine before the machine decides what question to ask it. And yet the answer still fits the question chosen at the end. This is the disturbing beauty of delayed choice physics. Not a proof that tomorrow can rewrite yesterday, but evidence that the past of a quantum particle may not contain the definite story your everyday intuition expects. In ordinary life, cause comes first and effect follows. A glass falls before it breaks. A match is struck before the flame appears, and a traveler chooses a road before arriving at a destination. You naturally assume that light must behave the same way, carrying a completed history behind it as it moves. John Archibald Wheeler challenged that assumption with an experiment built around a photon and two possible routes. The photon enters a device that divides its journey. At the far end, the experimenter may keep the routes separate and obtain information about which way the photon traveled, or recombine them and reveal an interference pattern associated with wave-like behavior. The decision can be made only after the photon has crossed the point where the paths divide. In carefully controlled experiments, even when the final arrangement is selected by a fast random process after the photon has entered the apparatus, the results still agree with the measurement eventually performed. When path information is available, the photon is detected in a way consistent with a distinguishable route. When the alternatives are recombined, many individual detections gradually produce interference. It is tempting to say that the later choice traveled backward and ordered the photon to change its earlier behavior. But the evidence does not require that conclusion. The experiment does not show a visible signal moving into the past, and it cannot be used to send a message to an earlier moment. Nothing already recorded is erased or replaced. The deeper lesson is that the photon may never have possessed the simple classical biography you were trying to assign to it. Before the measurement is completed, asking whether it really took one route or really traveled like a wave may be like asking which shape a cloud truly had before choosing the exact boundary by which you intend to measure it. Quantum theory predicts the probabilities of the final observations, but it does not always permit the particle to be described as a tiny object carrying fixed answers through every stage of the experiment. Later versions have strengthened this puzzle by moving the choice mechanism farther away, using single atoms instead of photons, and arranging the timing so that the measurement setting could not have influenced the particle through any ordinary signal after it entered the device. None of this proves that human consciousness creates reality. Detectors, switches, and physical interactions are enough. The universe does not need a person staring at the equipment, nor does it prove that the future controls the past in the dramatic sense of changing wars, preventing accidents, or repairing decisions already made. What it challenges is a quieter assumption that every event must possess a complete set of classical facts before those facts are measured. Some interpretations say the whole experiment should be treated as one connected quantum process, with no need to invent a definite path in the middle. Others explore models in which future measurement conditions help constrain earlier quantum descriptions, while still preventing messages or contradictions from traveling backward. The experimental results alone do not select one final interpretation, and researchers have shown that retrocausality is not required to explain the standard delayed choice arrangement. This leaves you in an unusual position. You are not being asked to believe that time runs backward. You are being asked to loosen the belief that reality is always assembled in the order you experience it. At the scale of human bodies, clocks, and memories, the past remains stable and causes still precede their consequences. But beneath that familiar layer, a quantum event may not divide cleanly into an independent beginning, middle, and end. Its meaning can depend on the complete arrangement through which it is finally revealed. The future may leave no message hidden in the past, yet the question chosen later can determine which past description is physically available. And perhaps that is the most unsettling possibility of all. Not that history changes, but that some parts of history were never fully written in the classical language you use to remember them. The quantum eraser. How information can change what the past appears to have been. A pattern can vanish without being destroyed, remain hidden inside randomness, and return only when the right pieces of information are placed beside each other. This is the central mystery of the quantum eraser, an experiment whose name sounds as though scientists are deleting the past, even though nothing already recorded is actually removed or rewritten. The experiment begins with light passing through two possible paths. When nothing reveals which path a photon could have taken, repeated detections can build an interference pattern, a sequence of brighter and darker regions created because the alternatives remain indistinguishable. But when the apparatus marks the paths in a detectable way, the pattern disappears. The photon does not need to be watched by a human, and no scientist needs to read the path record. It is enough that the information exists physically and could, in principle, distinguish one route from the other. The two alternatives have become connected to different states in the surrounding system, and the clear interference is lost. The quantum eraser asks what happens when that path information is made unavailable again. In early demonstrations, researchers marked the routes using properties such as polarization, and then measured the light in a different way, one that no longer revealed which route had been taken. When the results were sorted according to those measurements, interference returned within the selected groups. This confirmed a fundamental rule of quantum physics. Precise path knowledge and visible interference are complementary. The more clearly the paths can be distinguished, the less clearly the wave-like pattern can appear. The delayed choice version makes the situation feel far stranger. In the famous experiment reported by Yoon-Ho Kim and his colleagues in 2000, a device produced entangled pairs of photons. One photon, often called the signal photon, traveled toward a position-sensitive detector. Its partner, called the idler, followed a longer route through an arrangement that either preserved information about where the pair originated or mixed the alternatives so that this information could no longer be recovered. Because the idler traveled farther, the signal photon could be detected first. Only afterward would the partner encounter the part of the apparatus that determined whether the available measurement retained or erased the path distinction. This ordering invites a dramatic but misleading story. Perhaps the later measurement changes whether the earlier photon behaved like a wave or a particle, yet the actual data tell a more careful and more interesting story. If you look only at the signal detector, you never see a usable interference pattern. You see a broad distribution of individual points that looks the same regardless of what later happens to the idler. The earlier record does not visibly transform, and it contains no message from the future. The hidden structure appears only when researchers compare the two detector records and sort the signal detections according to how their partners were measured. One group produces an interference pattern, while another produces a complementary pattern with bright regions where the first has dark ones. When these groups are combined, the two patterns cancel, returning the featureless distribution that was present from the beginning. The experiment, therefore, does not restore a single pattern that had been physically erased. It reveals correlations that were invisible in the unsorted data. No observer at the first detector can know which later measurement occurred without receiving the partner results through ordinary communication. So the apparatus cannot send information backward in time or allow anyone to influence an event that has already been recorded. What changes is not the past itself, but the description you can construct from the complete set of evidence. Before the records are compared, each signal point appears isolated and random. After the matching idler result is known, that same point becomes part of a larger statistical pattern. Nothing about its position moves. Nothing is added to the old detector screen. The new information changes which relationship becomes visible. This is why the word eraser can be deceptive. The apparatus does not rub away a stored fact like ink from paper. It changes the basis in which the partner photon is measured, making path distinctions unavailable within particular correlated groups. The mystery lies not in destruction but in context. A result that appears meaningless alone can become highly ordered when paired with another result, much as scattered notes may sound like noise until you discover that they belong to two interwoven melodies. Yet even that comparison has limits, because the quantum pattern is not merely hidden by human ignorance. The entangled photons form one combined system, whose measurable properties cannot always be divided into independent stories for each photon. This teaches something deeper than the familiar idea that observation disturbs delicate particles. It shows that information is physical. The possibility of distinguishing alternatives affects which patterns nature allows, even when nobody opens a file, reads a display, or consciously learns the route. It also shows why facts in quantum physics are often facts about relationships rather than isolated objects. The signal photon alone does not carry the visible answer, and the idler alone does not carry it either. The structure exists in the correlations between them. You may be tempted to see this as proof that time runs backward, but the experiment gives no controllable retrocausal signal and no altered record of history. Its real challenge is quieter. It asks whether a quantum event should always be imagined as a tiny object completing a private journey, or whether the full meaning of that event belongs to a network of possible measurements and later comparisons. The past remains where it was, but what the past appears to contain can depend on which information you bring into relation with it. And perhaps that is why the quantum eraser feels so unsettling. It does not show that reality forgets what happened. It shows that reality may preserve its deepest order in connections that no single observation can reveal. The planet hidden inside Earth, vast oceans and unknown worlds beneath the surface. The largest hidden reservoir on Earth may be one you could never swim through, sail across, or even see as liquid water. Far beneath the crust, below the deepest mines, and beyond every hole humans have drilled, lies a region of the mantle capable of storing enormous quantities of water inside solid rock. It is sometimes described as an ocean beneath the surface, but this phrase can create the wrong picture. There are no vast blue caverns surrounding a secret inner planet, and no underground waves are breaking against buried shores. The water is locked into the atomic structure of minerals, held as hydrogen and hydroxyl within crystals compressed by pressures that would destroy any familiar landscape. This strange reservoir is concentrated especially within the mantle transition zone, a layer roughly 410 to 1660 kilometers below your feet. There, common upper mantle minerals transform into denser forms called wadsleyite and ringwoodite. Their crystal structures contain tiny defects where hydrogen can be stored, allowing the rock to behave like an immense mineral sponge without appearing wet. Laboratory experiments had suggested for decades that these minerals could hold significant water, but direct evidence arrived in an unexpectedly small package. A diamond brought to the surface from deep beneath Brazil. Trapped inside, it was a microscopic grain of ringwoodite containing enough hydrogen to show that at least part of the transition zone is genuinely hydrated. The diamond had acted like a sealed container, preserving a fragment of an environment that humans could never visit directly. If similar hydration exists across large areas, the transition zone could store an amount of water comparable to one or more surface oceans. Yet scientists still do not know how evenly that water is distributed. Some regions may be rich in it, while others may be surprisingly dry. and modern studies continue to produce different estimates for the global average. The source of this buried water is connected to a planetary circulation system far slower than clouds, rivers, and rain. At ocean trenches, one tectonic plate bends and sinks beneath another, carrying minerals that absorbed water near the seafloor. As the descending plate travels downward, heat and pressure reorganize those minerals. Some release their water, while others transport hydrogen deeper into the mantle. When hydrated ringwoodite is pushed below the transition zone and changes into minerals that cannot hold as much water, part of its stored hydrogen may be expelled, lowering the melting point of the surrounding rock and producing small regions of melt. Over immense spans of time, volcanoes can return some of this deep material toward the surface, linking the water in oceans and clouds to a hidden cycle that may take millions or even billions of years to complete. This deep reservoir matters because water changes the physical behavior of rock. Even small amounts can reduce its strength, alter how easily it flows, affect where melting begins, and influence the movement of tectonic plates. Water buried hundreds of kilometers down may therefore help shape earthquakes, volcanism, mountain building, and the long-term stability of Earth's surface oceans. The interior is not a frozen stack of layers, but a restless system of sinking slabs, rising hot material, mineral transformations, and chemical exchanges. Scientists map this world indirectly by studying how earthquake waves change speed and direction as they pass through it, much as doctors use waves to reveal structures hidden inside the body. These seismic images show enormous features: cold fragments of ancient plates descending into the mantle, broad regions where material moves differently from its surroundings, and boundaries where pressure forces minerals to rearrange themselves into entirely new structures. Yet those maps remain incomplete. Temperature, composition, and water can produce similar signals, making the deep Earth difficult to interpret with certainty. A region that looks unusual may be hotter, wetter, chemically different, partially melted, or some combination of all four. This is the real planet hidden inside Earth. Not a second globe with its own sky and continents, but an alien geological world occupying nearly everything beneath the thin surface where human history unfolds. Its minerals cannot remain stable at sea level. Its movements are measured in centimeters per year. Its landscapes are made not of open spaces, but of solid rock slowly flowing over geological time. You live on only the cooled outer skin of this world, while beneath you, water is carried through crystals, continents are recycled into the mantle, and fragments of ancient seafloor descend toward depths where their identity begins to disappear. The oceans above may feel permanent, yet their existence could be partly protected by this enormous interior exchange, with the mantle acting as both reservoir and regulator. Earth's habitability may depend not only on how much water arrived during the planet's formation, but on how effectively the interior has stored, released, and recycled it ever since. The deeper scientists look, the less Earth resembles a simple rocky sphere, and the more it appears to be a layered archive. Preserving material from vanished oceans and lost surfaces within minerals no human hand will ever touch. And perhaps the most humbling thought is that the familiar world of rain, rivers, and seas may be only the visible expression of a much older water system moving silently through the darkness below. Time crystals. Matter that repeats forever without moving through space. Strike a quantum system with the same perfectly timed pulse again and again, and it may answer in a slower rhythm of its own, as though matter has quietly refused to follow the clock controlling it. This is the defining behavior of a discrete time crystal, one of the strangest phases of matter created in modern laboratories. The name can be misleading because a time crystal is not a jewel that travels through time, and its particles are not endlessly circling through space. Instead, an internal property of the system, often the direction of many interacting quantum spins, repeats in a stable pattern over time. To understand why this deserves to be called a crystal, consider what makes an ordinary crystal special. The atoms in salt or diamond are arranged in a repeating spatial pattern, so moving a small distance through the material reveals the same structure again. A time crystal transfers this idea from space to time. Its observable state returns again and again at regular intervals. But the repetition is not simply copied from the external rhythm driving it. Suppose a series of pulses reaches the system once every second. A normal response might repeat once every second as well. A discrete time crystal can respond only once every 2 seconds, flipping into one state after the first pulse and returning after the next. The drive has one rhythm while the matter chooses a larger repeating cycle. This is known as breaking time translation symmetry. The physical laws imposed by the pulses repeat at one interval, but the system settles into a different and more extended temporal pattern. In 2017, researchers observed this behavior in 2 very different experimental platforms. One team used a chain of trapped ytterbium ions whose quantum spins interacted with one another, while another studied roughly 1 million spin impurities inside diamond. In both cases, the collective oscillation remained locked to its own rhythm even when the driving pulses were slightly imperfect, showing that the pattern was not merely a fragile accident or a finely tuned echo. This resistance to small disturbances is essential. A collection of independent particles can also oscillate, but tiny errors soon push them out of step. In a time crystal, interactions cause the components to organize collectively. One spin influences another, and the many-body system maintains a shared rhythm that survives imperfections, which would normally destroy ordinary oscillations. Disorder can also help by preventing the system from rapidly absorbing energy and heating into a featureless state. Without such protection, repeated driving would gradually erase the organized behavior, just as constant shaking eventually mixes a carefully arranged container. Time crystals therefore exist outside ordinary thermal equilibrium. They are not motionless objects, resting at their lowest energy, but organized dynamical phases maintained under carefully controlled conditions. This point corrects one of the most common exaggerations surrounding them. A time crystal is not a perpetual motion machine. It cannot provide unlimited useful energy, power a device forever, or violate thermodynamics. The word forever refers to the ideal mathematical phase, in which the repeating order can persist indefinitely if the system is perfectly isolated and the necessary conditions remain intact. Real experiments are always limited by noise, imperfect controls, environmental contact, and the finite time available for observation. The system may repeat without consuming energy in the way a motor burns fuel on every cycle, but preparing, controlling, and measuring it still requires laboratory equipment and external energy. Later experiments used programmable quantum processors to examine time crystalline order in highly controlled arrays of qubits. Google's Sycamore processor, for example, allowed researchers to prepare an interacting system, disturb it deliberately, and test whether its repeating pattern remained stable rather than slowly drifting away. The results provided strong evidence for a genuine many-body phase, rather than a collection of unrelated oscillators that merely happened to move together for a short time. Other experiments have found pre-thermal and dissipative forms of time crystalline behavior, showing that there is more than one physical route to stable order in time. In some systems, the structure survives for an extremely long period before heating finally wins. In others, carefully balanced interactions with the environment help sustain the oscillation. These variations are still active areas of research, and physicists continue debating which observations deserve the strictest time crystal label and how broadly the concept should be extended. What makes the discovery important is not that scientists have found matter escaping time, but that they have expanded the meaning of a phase of matter. Ice, water, magnets, and superconductors are distinguished by how large numbers of particles organize themselves. Time crystals reveal that organization does not need to be frozen into a spatial arrangement. Matter can also form order through repetition, creating a phase defined by when its state returns, rather than where its atoms sit. This may eventually help researchers study quantum memory, precision sensing, and the stability of complex quantum systems, although practical technologies are not yet guaranteed. The deeper lesson is already clear. Repetition is not always passive obedience. When many quantum components interact, they can take an imposed beat and transform it into a new rhythm that belongs to the system as a whole. Nothing visible needs to rotate, travel, or trace a circle through space. The change occurs within the state of matter itself, returning with a regularity that remains steady even when the outside timing is imperfect. And so a time crystal does not stand outside the flow of time. It reveals that time can become part of matter's architecture, a direction in which order can form, persist, and quietly repeat. Rogue worlds without suns, planets drifting alone through eternal night. Somewhere between the stars, entire worlds may be crossing the galaxy without ever seeing a sunrise. These are rogue planets, bodies with planetary masses that travel without being gravitationally bound to any star, moving through the Milky Way under the broader pull of the galaxy itself. They are often pictured as frozen Earths violently expelled from their homes, and some may indeed have begun inside young planetary systems. During the chaotic early life of a system, giant planets can disturb smaller neighbors, changing their orbits until one is thrown beyond the star's gravitational control. A passing star can produce the same result, and the death of a host star may also release planets into interstellar space. Yet exile is not their only possible origin. Some planetary mass objects may form directly from collapsing clouds of gas, more like miniature failed stars than abandoned planets. While simulations suggest that violent encounters between young systems can create dense streams of material that fragment into free-floating worlds. This means the name Rogue Planet may hide several different histories beneath one dark appearance. Some were born beside a sun and lost it. Others may never have belonged to one at all. Finding them is difficult because an old rogue planet produces almost no visible light. A planet orbiting a star can reveal itself by dimming that star or pulling it slightly from side to side. But a solitary world offers no bright companion against which its presence can be measured. Astronomers often discover candidates through gravitational microlensing. When an unseen planet passes almost perfectly in front of a distant star, its gravity briefly bends and magnifies the background starlight. The planet itself remains invisible, but for a few hours or perhaps a day, it leaves a temporary brightening in the sky. The alignment is unlikely to repeat, so the observation must be captured while it is happening. Young and massive free-floating objects can sometimes be seen directly in infrared light because they still glow with heat left from their formation, although separating the lightest brown dwarfs from the heaviest rogue planets can be difficult. In 2023, the James Webb Space Telescope identified a free-floating brown dwarf, estimated at only 3 to 4 times Jupiter's mass, showing how blurred the border between a small star-like object and a giant planet can become when there is no host star to reveal how it formed. Life on such a world would appear almost impossible at first. Without sunlight, its surface would cool, oceans would freeze from above, and ordinary photosynthesis would have no steady source of energy. But darkness does not always mean complete lifelessness. A rocky rogue planet could retain heat from radioactive elements and from energy stored during its formation. If it possessed a thick atmosphere rich in hydrogen, that atmosphere might trap enough internal warmth to keep surface conditions far warmer than empty space would suggest. Even without such an atmosphere, a deep ocean might survive beneath a protective shell of ice, heated from below by the planet's interior. Any ecosystem there would need to depend on chemical energy rather than daylight, perhaps resembling communities around hydrothermal vents on Earth, where organisms live from reactions between water and hot rock. These possibilities remain theoretical. No inhabited rogue world has been found, and scientists do not yet know how often such planets retain atmospheres, oceans, active interiors, or moons. Their total number is also uncertain because the smallest and coldest examples are the hardest to detect. Future microlensing surveys are expected to reveal many more, including worlds with masses below that of Earth, allowing astronomers to test whether planetary systems commonly lose their children during formation. NASA studies have estimated that the Roman Space Telescope could detect hundreds of Earth-mass rogue planets, but the true population will only become clearer after a wide and systematic survey is completed. A rogue planet is therefore not simply a dead rock wandering through an empty void. It may carry an atmosphere from a vanished beginning, moons that remained bound during its escape, buried water protected beneath kilometers of ice, or geological heat that continues long after the last direct sunlight has faded. It could pass through the outer regions of another planetary system and leave again without being captured, spending billions of years between brief encounters with stars. From its surface, the sky would not glow with daylight or display a familiar sun. The stars would remain sharp and unmoving through an endless night, while the planet's only warmth rose from within. Such worlds challenge the quiet assumption that planets naturally belong to stars. A star may illuminate a planet, shape its seasons, and dominate its sky, but it does not define what a planet is. Some worlds may spend their entire existence without an orbit they can call home, carrying their private geology through the darkness and reminding you that even in astronomy, belonging is not guaranteed by birth. The hidden ocean worlds of the solar system, where alien life may be waiting. The most promising seas beyond Earth are hidden beneath landscapes where no rain falls, no wind moves, and sunlight never touches the water. Across the outer solar system, several frozen moons appear to conceal enormous oceans below their icy surfaces, transforming places once dismissed as lifeless balls of rock and frost into some of the most compelling environments in the search for alien biology. Europa, one of Jupiter's large moons, offers one of the clearest examples. Its surface is crossed by long reddish fractures and broken regions where blocks of ice seem to have shifted, rotated, and frozen again, suggesting that the shell above the ocean may still be geologically active. More direct evidence came from NASA's Galileo spacecraft, which detected a changing magnetic signature best explained by a global layer of electrically conductive material beneath the surface, most likely a salty ocean. Scientists estimate that Europa may contain more liquid water than all of Earth's oceans combined, even though the entire sea is sealed below an ice shell whose exact thickness remains uncertain. Jupiter's gravity continually stretches and compresses the moon as it moves through its orbit, generating internal heat that helps prevent the buried ocean from freezing completely. Yet Europa is not alone. Around Saturn, the small moon Enceladus openly reveals what Europa keeps concealed. Great fractures near its south pole release jets of water vapor and ice grains into space, allowing spacecraft to sample material from a subsurface ocean without drilling through the crust. NASA's Cassini probe repeatedly flew through these plumes and found salts, organic compounds, carbon dioxide, methane, ammonia, molecular hydrogen, and tiny silica particles. Together, these materials indicate that liquid water is interacting with warm rock on the ocean floor, producing chemical reactions capable of releasing usable energy. Scientists have also detected phosphates in plume particles, showing that phosphorus, an element essential to life on Earth, is likely abundant in the ocean. None of these discoveries proves that organisms exist there, because organic chemistry and biological activity are not the same thing, but they demonstrate that Enceladus possesses several ingredients considered important for habitability: water, complex chemistry, internal energy, and contact between the ocean and a rocky seabed. Ganymede, the largest moon in the solar system, may hide an ocean even deeper below its surface. Its internal structure could include several layers of liquid water separated by different forms of high-pressure ice, creating a vast underground arrangement unlike any sea on Earth. Ganymede also possesses its own magnetic field, a feature unique among moons, and subtle changes observed within that field support the existence of salty water below the crust. Callisto, another moon of Jupiter, may also contain a buried ocean, although its ancient and heavily cratered surface shows far less geological activity. Saturn's Titan presents an even stranger variation. Above ground, it has clouds, rivers, rain, and lakes made of liquid methane and ethane, while a separate ocean of water is believed to exist far below the frozen crust. However, an ocean alone does not guarantee habitability. If thick layers of high-pressure ice separate the water from the rocky interior, the ocean may receive fewer minerals and less chemical energy, reducing the opportunities for life to emerge. This is why scientists do not simply ask where liquid water exists. They ask whether the water interacts with rock, whether useful elements can circulate through it, whether energy remains available over long periods, and whether the chemistry stays stable enough for increasingly complex reactions to develop. ESA's JUICE mission is designed to investigate Ganymede, Europa, and Callisto as ocean-bearing worlds, while NASA's Europa Clipper will conduct dozens of close passes of Europa to examine its ice, composition, geology, gravity, and possible connections between the surface and the ocean below. Europa Clipper is not designed to announce the discovery of life. Its central task is to determine whether environments capable of supporting life exist beneath the ice. Reaching the oceans themselves remains an enormous challenge. Europa's surface is exposed to intense radiation from Jupiter, and drilling through many kilometers of ice would require technology able to operate for years without contaminating the environment it was sent to study. Enceladus may offer an easier path because its plume naturally carries ocean material into space. But even there, detecting a molecule associated with life would not be enough. Scientists would need to rule out non-living chemical processes and look for several independent signs that point toward the same biological explanation. Until then, the most honest conclusion is also the most fascinating. No alien organism has been found in any hidden ocean. Yet the solar system contains multiple worlds where liquid water has probably survived for billions of years beneath protective ice. These discoveries have changed the traditional idea of a habitable world. A planet or moon may not need warm sunlight, green continents, or an open surface ocean. Life, if it exists elsewhere, could remain entirely hidden, sustained by chemistry in a darkness that has never known day. And while those buried seas may appear silent from above, they force you to reconsider where a living world truly begins. Not at the surface where it can be seen, but wherever matter, energy, and time are quietly given enough opportunity to become something more. The last map of reality. Why we may never see beyond the cosmic horizon. No telescope, however powerful, can photograph a place whose information has never had enough time to reach you. This is the hidden limit behind every map of the cosmos. The observable universe is not the whole universe, but only the region from which light or another physical signal has been able to arrive since cosmic expansion began. The universe is about 13.8 billion years old, yet the present distance to the most remote regions we can observe is roughly 46 billion light-years in every direction, because space continued expanding while their light traveled toward us. This creates a vast sphere of visibility around your location, commonly called the cosmic or particle horizon. It may sound like an edge, but there is no glowing wall waiting at the boundary, and no reason to think space ends there. An observer in a distant galaxy would possess a different observable sphere centered on their own position. Earth appears to sit at the middle only because every view of the universe is naturally centered on the observer receiving the signals, much as the horizon on an open sea seems to surround every ship without proving that any ship occupies the center of the ocean. The distinction matters because maps can quietly create the illusion that what has been mapped is all that exists. Astronomers chart galaxies through visible light, infrared radiation, radio waves, X-rays, gravitational effects, and other messengers, but every method remains limited by causality. A better detector can reveal a fainter signal, resolve a smaller object, or extract information that older instruments missed. It cannot collect a message that has not arrived. Even gravitational waves and neutrinos cannot provide a route around this fundamental restriction, because they also move through space-time and must reach an instrument before they can tell you anything. The horizon is therefore not a failure of engineering. It is built into the history and geometry of the universe. Cosmic expansion adds an even more haunting limit. Light from distant galaxies is stretched to longer wavelengths as space grows, a process known as cosmological redshift. Because the expansion is currently accelerating, there are remote regions visible through ancient light whose present-day events may never reach us, no matter how long future astronomers continue watching. The photons arriving now began their journeys when those galaxies were much closer, but signals emitted there today may be carried away by expanding space faster than they can reduce the growing distance. This does not mean the galaxies themselves locally break the speed limit of light. The space between large unbound regions is expanding, and relativity allows that distance to increase at a rate greater than light could cross. Over immense time, more galaxies outside our gravitationally bound neighborhood are expected to fade, redden, and pass beyond practical observation, leaving future observers with a smaller visible record of the wider cosmos. The universe may contain enormously more space than the observable region, and it may even be infinite, but present measurements cannot settle the question. Observations indicate that space is very close to geometrically flat on the largest scales, yet a surface can appear flat across a limited region while belonging to something much larger, just as a small patch of Earth does not reveal the planet's full curvature. Inflationary models suggest that the universe could extend vastly beyond the territory accessible to us, but the unseen part cannot be directly mapped unless it has left an observable influence inside our horizon. Scientists can test models, search for subtle signatures, and determine which possible universes agree with the evidence, but inference is not the same as sight. Beyond a certain point, several different cosmic realities may produce the same view from inside our limited sphere. This creates a form of permanent ignorance unlike an ordinary unanswered question. A hidden planet can eventually be approached, a buried structure can be excavated, and a faint object can be revealed by a larger telescope. The region beyond the cosmic horizon may remain inaccessible, not because it is too dark or too distant for current technology, but because no information from it can ever enter the part of space-time connected to us. You may live inside a universe far larger and stranger than any final atlas could contain, surrounded by regions whose galaxies, histories, and physical conditions will never become part of human knowledge. The last map of reality may therefore end not with a discovered shoreline, but with a quiet circle marking where evidence stops. Beyond it, space may continue without limit, filled with structures no eye will meet and events no instrument will record. And the deeper lesson is not simply that the universe is enormous, but that reality and observable reality are not the same thing. One describes everything that exists, while the other describes the small portion existence has been able to tell you about. Cosmic strings, ancient cracks that may still run through the universe. The universe may still carry scars from a moment when its laws were choosing what form to take. Cosmic strings are hypothetical structures that could have formed during extremely early phase transitions, when the expanding cosmos cooled and fields that had once been uniform settled into new states. They are often described as cracks in space, but this image must be handled carefully. A cosmic string would not be an empty cut, a tunnel or a tear through which something could fall. It would be a narrow concentration of energy, a one-dimensional topological defect produced because distant regions of the young universe could not coordinate how they entered the new physical state. A simple comparison is the formation of cracks in freezing water. Different patches of ice begin arranging themselves independently, and where their structures fail to match, a lasting boundary can remain. In the early universe, the mismatch would not occur between pieces of ice, but within fundamental fields filling all of space. If the geometry of those fields forced the defect to remain, the result could be a thread of trapped energy extending across astronomical distances. Such defects are predicted by some theories that attempt to describe physics at energies far beyond anything human machines can create. Although no cosmic string has ever been confirmed, a string could be extraordinarily thin while possessing immense energy along every unit of its length. This energy would give it tension, causing curved strings to straighten and closed loops to contract. Yet a long string would not necessarily disappear. Simulations suggest that a network could evolve as the universe expands, with strings moving, crossing, and reconnecting. When two sections intersect, they may exchange partners, cutting off loops from the larger network. Those loops could oscillate at enormous speeds, repeatedly changing shape as tension pulls them inward. Certain points called cusps may briefly approach the speed of light, while sharp bends known as kinks can travel along the string. These violent motions are expected to release energy, potentially including bursts and a persistent background of gravitational waves. Because those waves could survive from eras too early to be observed with ordinary light, cosmic strings would act like ancient instruments still vibrating after the event that created them. Searchers by LIGO, Virgo, and CAGRA have looked for both individual bursts and the combined gravitational wave background predicted by string networks. So far, no signal has been identified as evidence of cosmic strings, and the absence of a detection has instead allowed physicists to rule out or restrict many versions of the idea. Analyses using observations through the first half of the fourth observing run continue to report no detectable early universe gravitational wave background, placing stronger limits on possible cosmic string models. Their gravity would also behave in an unusual way. A massive star bends light because its gravity curves space-time around a concentrated object. A long, straight cosmic string would create something closer to a missing wedge in the geometry around it. Space could remain locally almost flat, yet a complete circle around the string would contain slightly less angle than expected. Light traveling on opposite sides could then reach an observer along two routes, producing nearly identical images of the same distant galaxy. Unlike many ordinary gravitational lenses, a cosmic string might create a distinctive pair without strongly magnifying or distorting the source. A moving string could also leave a thin discontinuity in the temperature of the cosmic microwave background, with photons on one side shifted differently from those on the other. Astronomers have searched for these paired images and line-like signatures, while measurements from the Planck mission have placed strict limits on how much cosmic strings could have contributed to the patterns in the oldest observable light. The data show that ordinary primordial density variations, rather than strings, produced most of the structure seen in the universe, but they do not eliminate every possible type or energy scale of string. This is important because the phrase cosmic string can refer to more than one theoretical origin. Field theory strings could emerge from symmetry-breaking transitions, while cosmic superstrings might be enormous versions of the fundamental strings proposed in certain models of particle physics and extra dimensions. These possibilities could differ in how easily strings reconnect, how many kinds exist, and what gravitational signals they produce. Detecting one would therefore reveal far more than an unusual object in space. It could provide direct evidence that the early universe passed through a hidden phase transition, expose physical laws operating at unreachable energies, or offer clues about dimensions and fields that remain invisible in ordinary experiments. A string crossing a galaxy would not slice stars apart like a wire, and it would not create a glowing line visible to the naked eye. Its influence would be gravitational, expressed through the paths of light, the motion of surrounding matter, and waves traveling through space-time. A rapidly moving string could pull material toward the region behind it, producing an extended wake where matter becomes slightly denser. In the past, cosmic strings were considered possible seeds for galaxies and large-scale structure, but precise observations now show that they cannot be the main explanation for how cosmic structure formed. Their modern value lies elsewhere. They are possible fossils of fundamental physics, preserved not inside rock, but within the shape of fields themselves. This makes the search unusually difficult. A candidate pair of galaxies can turn out to be two separate objects. A gravitational wave background can be produced by merging black holes rather than ancient defects. A pattern in cosmic radiation can arise from noise, foreground material, or statistical chance. Scientists must therefore search for several compatible signatures, rather than allowing one dramatic image to become proof. The correct conclusion today is not that cosmic strings run through the universe, but that credible theories allow them, observations increasingly restrict them, and a narrow range of possibilities remains open. Their existence would mean that emptiness is capable of retaining structure, and that a transition lasting only a fraction of the universe's first second could leave a physical mark stretching across billions of years. You would never touch such a scar or see its surface, because it would not be made from atoms at all. It would be a surviving failure of perfect alignment, a place where the young universe could not smoothly agree with itself. And perhaps this is what makes cosmic strings so compelling. They suggest that even the laws of nature may have a history, and that somewhere in the darkness, the universe may still be carrying the seams from the moment it became the reality you now inhabit. The dark matter wind, the invisible current, Earth may be moving through. At this moment, Earth may be cutting through an invisible current of matter that fills the Milky Way, yet neither your skin nor the planet beneath you can feel it passing. Physicists call this predicted flow the dark matter wind, although it is not wind in the ordinary sense. No air is moving, no pressure is building, and nothing is brushing against the atmosphere. The idea comes from the evidence that our galaxy is surrounded by a vast halo of unseen mass whose gravity influences the motion of stars and helps hold the Milky Way together. If part of this dark matter consists of particles moving throughout that halo, then the solar system's journey around the galactic center should make those particles appear to arrive from a preferred direction, much as rain seems to strike the front window of a moving car, even when it is falling almost vertically. Under the simplest model, the apparent current comes roughly from the direction of the constellation Cygnus, not because Cygnus is producing dark matter, but because the Sun is moving through the galactic halo toward that region of the sky. Earth adds a second motion to this journey. As it travels around the Sun, its orbital speed sometimes points partly in the same direction as the Sun's galactic motion, and sometimes partly against it. If the particle wind picture is correct, a detector on Earth should therefore encounter a slightly stronger flow during part of the year and a slightly weaker one roughly 6 months later. In the standard version of the model, the expected interaction rate usually reaches its maximum near the beginning of June and its minimum near the beginning of December, although streams, clumps, or different dark matter properties could shift the timing and shape of the variation. This seasonal rise and fall is known as annual modulation, and it offers scientists something more valuable than a simple collection of unexplained impacts. A repeating signature connected to Earth's motion through the galaxy. The search takes place in laboratories buried beneath mountains or deep underground, where thick layers of rock block much of the cosmic radiation that would otherwise imitate a dark matter signal. Inside these facilities, tanks of liquid xenon, argon, or carefully purified crystals wait for an exceptionally rare collision. If a suitable dark matter particle struck the nucleus of an atom, the nucleus might recoil slightly, producing tiny flashes of light, released electrons, or vibrations that sensitive instruments could record. Most hypothetical particles would pass through the entire planet without interacting at all, so the challenge is not to stop the wind, but to recognize one authentic touch within an enormous background of natural radioactivity. Detector noise, neutrons, and neutrinos. One experiment, Dharma, Libra, has reported a long-running annual variation with timing broadly similar to the expected modulation. But that result has not become an accepted dark matter discovery. Other experiments using the same sodium iodide material, including NAS-112 and Cosine-100, have not found supporting evidence for the claimed dark matter modulation, and their combined analyses continue to place the interpretation under serious pressure. Meanwhile, enormous detectors searching for the type of particle known as a WIMP have become increasingly sensitive without producing a confirmed excess. The Elux-Zeppelin experiment's multi-ton xenon search found no evidence above its expected backgrounds, eliminating more of the territory where these particles might have been hiding, but leaving many other dark matter possibilities open. The absence of a detection does not mean the galactic halo is imaginary. It means that dark matter may interact even more weakly than expected, may have a mass outside the range of present instruments, or may not be made of WIMPs at all. It could involve ultralight particles behaving more like fields, heavier hidden objects, several components mixed together, or physics that current experiments were never designed to detect. Even the smooth wind itself is an approximation. The Milky Way has grown by absorbing smaller galaxies, and remnants of those collisions may have left streams of dark matter crossing the solar system at distinct speeds and angles. A real detection could therefore reveal not just a new particle, but part of the galaxy's forgotten history. The strongest future proof may come from direction rather than season. Because Earth rotates each day, a laboratory's orientation changes continuously relative to the predicted incoming flow. A detector capable of reconstructing the direction of each recoiling nucleus could watch the preferred direction move across its local sky while remaining aligned with the solar system's motion through the galaxy. Ordinary radioactive backgrounds should not imitate that celestial pattern easily, making a directional signal one of the clearest ways to show that the impacts truly came from beyond Earth. Projects such as Cygnus are exploring gas-filled detectors designed to preserve these tiny recoil tracks instead of recording only their energy. For now, the dark matter wind remains a prediction rather than an observed current. No instrument has yet produced a signal that the scientific community accepts as direct detection of galactic dark matter. Still, the idea changes the way you can picture your place in the Milky Way. You are not sitting motionless beneath a fixed night sky. You are traveling with the sun through a gravitational landscape shaped mostly by something unseen. If the particle picture is correct, that hidden material passes through the atmosphere, the oceans, the walls around you, and the atoms of your body while leaving almost no trace. The planet may already be immersed in the evidence, yet the evidence is so quiet that discovering it requires listening for movements smaller than anything your senses evolved to notice. And perhaps that is the final challenge of the dark matter wind. The universe may be touching you continuously, while revealing its presence only through the rarest possible collision. The invisible web between galaxies, the hidden structure holding the universe together. Galaxies do not float through the universe like randomly scattered islands. They gather along immense hidden highways whose full shape only becomes visible when millions of cosmic positions are viewed together. This structure is known as the cosmic web, a vast arrangement of filaments, sheets, dense knots, and enormous voids stretching across hundreds of millions of light years. Galaxies and galaxy clusters occupy its brightest intersections, but the web itself is far larger than the objects that make it visible. Its origin can be traced to the young universe, when matter was distributed almost evenly but not perfectly. Tiny variations meant that some regions contained slightly more material than others. Their stronger gravity slowly attracted surrounding matter, making the dense regions denser, while emptier regions lost more of what they contained. Over billions of years, this uneven collapse did not produce a simple collection of spherical clumps. Matter flowed along preferred directions, first forming broad sheets, then narrow filaments, and finally crowded nodes where multiple strands met. This is why the universe resembles a sponge or a nervous system when mapped on its largest scales. Bright clusters form the concentrated junctions. Long chains of galaxies trace the strands, and vast cosmic voids lie between them. Yet the visible galaxies reveal only part of the structure. Much of the web consists of diffuse gas and unseen mass spread too thinly to shine like a star or galaxy. The gas inside many filaments can be heated to hundreds of thousands or millions of degrees as it falls inward and is compressed by gravity. But because it is extremely sparse, it remains difficult to detect even when it is very hot. Astronomers call much of this material the warm-hot intergalactic medium, and it may contain a significant fraction of the ordinary matter that seem to be missing from inventories of the nearby universe. X-ray observations have revealed hot gas extending along filaments near massive clusters. including a recently studied structure connecting 4 clusters whose gas may account for part of this long-sought material. Scientists uncover the web through several indirect methods. They map the 3-dimensional positions of enormous numbers of galaxies, looking for elongated concentrations and empty regions. They study how foreground matter bends the light of more distant galaxies, allowing gravity to expose mass that emits little or no light. They examine the spectra of bright quasars, where intervening hydrogen leaves a sequence of absorption marks that traces diffuse gas across deep space. More recently, fast radio bursts have become valuable probes because their brief radio signals are delayed by free electrons encountered during their journey, allowing astronomers to estimate how much thinly spread matter lies between galaxies. Studies using these bursts indicate that much of the ordinary matter outside galaxies is distributed through the diffuse intergalactic medium, strengthening the picture of a gas-rich cosmic web rather than a universe made only of bright, isolated systems. The web does more than arrange galaxies after they form. Its environment can influence how they grow. Gas flows along filaments toward denser nodes, helping supply galaxies with material from which new stars may form. Galaxies near crowded intersections experience more encounters, mergers, and environmental pressure than galaxies located beside quieter strands or within underdense regions. Their shapes, rotation, star formation, and available gas can therefore be connected to where they live within the larger network. Even the orientation of a galaxy may preserve traces of how matter flowed into its region over cosmic history. The web is not a rigid frame holding the universe in place, and its filaments are not solid cables. It is an evolving pattern created by gravity, continuously shaped as matter moves, structures merge, and cosmic expansion increases the distance between regions that are not gravitationally bound. Some strands feed growing clusters, while voids become increasingly empty as material drains toward their boundaries. The largest known structures are therefore not single objects in the ordinary sense, but connected patterns emerging from countless gravitational relationships. This changes how you can picture the night sky. Each galaxy that appears alone may belong to a filament extending far beyond what the eye can follow, and each apparently empty gap may be part of a void whose size exceeds any familiar scale. The universe is not mainly a collection of separate lights surrounded by meaningless darkness. It is a structured landscape whose brightest objects reveal only the peaks of a much deeper distribution. And once you understand that hidden architecture, isolation begins to look like an illusion of limited vision. Galaxies may be separated by unimaginable distances, yet their positions, histories, and futures remain written into the same enormous web. The strange intelligence of slime mold, a brainless organism that solves complex problems. A living yellow network can escape a maze, redesign itself when conditions change, and remember where it has already been. Even though it has no brain, no neurons, and not a single organ for thought. This organism is Physarum polycephalum, a species commonly called slime mold, although it is neither an animal, a plant, nor a true fungus. During the stage, most often studied in laboratories, it exists as one enormous cell containing many nuclei, spreading across damp surfaces as a shifting web of soft tubes. It has no central commander telling one region what the others are doing. Instead, its entire body senses chemicals, moisture, light, temperature, and food, then changes its shape through rhythmic waves of contraction that move fluid back and forth through the network. Those pulses allow information about one part of the organism to influence distant parts, creating coordinated behavior without anything resembling a nervous system. Its most famous demonstration began inside a maze. Researchers allowed Physarum to spread throughout the available passages, then placed food at 2 separate locations. The organism gradually withdrew from unproductive dead ends while maintaining a connection between the food sources, eventually concentrating its body along the shortest available route. It did not inspect the maze from above, calculate every possibility, or construct an internal map like a human solving a puzzle. It explored many routes at once, then strengthened the tubes carrying useful flows while allowing inefficient branches to shrink. The solution emerged from the repeated adjustment of the body itself. This process becomes even more remarkable when several food sources are scattered across a surface. Physarum initially creates a dense network connecting them, but supporting every branch costs energy. Over time, heavily used tubes widen, poorly used connections disappear, and the network becomes a compromise between efficiency, total length, and resilience. In a well-known experiment, researchers placed food in positions corresponding to cities around Tokyo and exposed parts of the surface to conditions representing geographical obstacles. The slime mold developed a transport network with striking similarities to the human-designed rail system, balancing short routes with backup connections. This did not mean that the organism understood cities or engineering. It meant that natural selection had equipped it with simple local rules capable of producing solutions to problems that humans also face. How to connect many important locations without wasting too many resources or making the entire network vulnerable to a single break. The intelligence, if the word is used at all, belongs less to a hidden mind than to a self-correcting process distributed across the organism's changing form. Physarum can also use its environment as a kind of external record. As it travels, it leaves behind a transparent layer of slime. Experiments have shown that it tends to avoid areas already marked by this material, helping it distinguish explored territory from unfamiliar ground and navigate around obstacles more effectively. Its memory is not necessarily stored in a brain-like representation of space. Part of it is written directly onto the surface beneath its body. The landscape becomes a notebook, and the organism reads the traces of its own movement by responding differently when it encounters them again. Internal changes may preserve information as well. Nutrients can alter the thickness of nearby tubes, leaving a temporary imprint in the hierarchy of the network that influences later movement. In this sense, the body is not merely carrying information, it is physically reshaped by what has happened to it. Researchers have also tested whether Physarum can display habituation, one of the simplest forms of learning. In these experiments, the organism had to cross a bridge containing an unpleasant but harmless substance to reach food. At first, it moved slowly and cautiously, but after repeated exposures it crossed more readily, as though it had learned that the substance was not truly dangerous. After a period without exposure, the cautious response returned, suggesting that the change was not simple exhaustion or permanent damage. Such results do not prove that slime mold experiences fear, makes conscious decisions, or understands what it is doing. Words like learning, memory, and problem-solving describe observable changes in behavior, not evidence of an inner world like your own. Scientists still debate how far cognitive language should be extended to organisms without nervous systems, and some claims about slime mold intelligence have been criticized for turning adaptive biological mechanisms into dramatic stories. The safer conclusion is also the more educational one. Complex behavior does not always require a complex control center. Many useful outcomes can arise when simple components exchange signals, respond to feedback, preserve traces of previous conditions, and continuously adjust to their surroundings. Your own brain gathers information through specialized cells and concentrates much of its processing within neural networks. Physarum follows another design. Sensing, movement, storage, and decision-like behavior are spread across a living body that constantly rebuilds itself. There is no single place inside it where the solution appears. The solution is the pattern of growth, the direction of flow, and the disappearance of paths that no longer serve a purpose. This challenges the instinct to treat intelligence as a substance that either exists fully or does not exist at all. Perhaps nature offers a spectrum of information processing strategies, from chemical feedback in cells to nervous systems capable of language and reflection. Slime mold does not secretly possess a tiny mind, but it demonstrates how much can be achieved before anything like a mind evolves. It finds order through movement, stores history and structure, and reaches workable answers without ever seeing the problem as a whole. And as you watch this brainless cell reshape itself around each obstacle, The deeper question is no longer whether it thinks like you, but how many forms of intelligence you have failed to recognize simply because they do not think from one central place. The quantum compass inside animals, how birds may see Earth's magnetic field. A night-flying bird may cross a continent by responding to chemical reactions inside its eyes that are altered by a force thousands of times weaker than a refrigerator magnet. This possibility lies at the heart of the avian magnetic compass, a sensory system that allows many birds to extract direction from Earth's magnetic field when stars, landmarks, and the sun are unavailable. Behavioral experiments have shown that migratory songbirds can still choose seasonally appropriate directions inside controlled rooms where researchers rotate the surrounding magnetic field, causing the birds to turn with it even though nothing visible in the room has changed. Their compass is unusual because it does not appear to work like the needle in your hand. A conventional compass distinguishes magnetic north from south, but many birds use an inclination compass, sensing the angle at which field lines slope toward or away from Earth's surface. This tells them which direction leads toward the nearest magnetic pole and which leads toward the equator, without labeling one end of the field as north. If researchers reverse the vertical angle of the artificial field while preserving its general alignment, the birds often reverse their chosen direction, revealing that they are reading the field's geometry rather than following a hidden magnetic needle. The leading explanation places part of this sense inside the retina, where light-sensitive proteins called cryptochromes may convert magnetic direction into a biological signal. When blue or green light activates a suitable cryptochrome molecule, an electron can move through the protein, briefly creating two chemically linked particles with unpaired electrons. These form what physicists call a radical pair. The pair can exist in different quantum spin arrangements, and Earth's magnetic field may slightly alter how those arrangements change into one another. Different spin histories can lead to different chemical products, so the direction of the molecule relative to the field could influence the strength of the signal eventually sent to the nervous system. Laboratory work with artificial molecular systems has shown that radical pair chemistry can respond directionally to magnetic fields within the same weak range as Earth's, demonstrating that a chemical compass is physically possible rather than merely an elegant theory. Cryptochrome 4 has attracted particular interest because it is found in bird retinas and can undergo the light-driven electron transfers required to create long-lived radical pairs. Experiments on pigeon cryptochrome have confirmed that the protein can form magnetically relevant light-induced states, but scientists have not yet demonstrated the entire pathway from a specific cryptochrome molecule inside a living bird to a conscious sense of direction. The identity of the primary receptor, the molecules that carry its signal, and the exact neurons that interpret it remain unresolved. This uncertainty is especially important when people say that birds can see magnetic fields. One plausible model suggests that cryptochromes are arranged in the retina so that their chemical responses vary with the orientation of the bird's head. The resulting signal might add a faint pattern of brightness, color, shadow, or contrast to the normal visual scene. As the bird turns, the pattern would shift in a predictable way, providing a stable axis that could guide flight. It might resemble a soft, dark region, a pair of symmetrical shapes, or a change in visual texture aligned with the field. But these descriptions are theoretical reconstructions, not reports from the birds themselves. Researchers cannot ask a robin what the field looks like, and the magnetic information could instead travel through a separate neural channel that only interacts with vision without becoming a literal overlay. What is known is that the compass of many tested birds depends on suitable light conditions and can be disrupted by weak radio frequency fields under some experimental arrangements, findings broadly compatible with a light-driven radical pair mechanism. Yet the effects vary with frequency, intensity, species, and laboratory conditions, and some studies have produced results that are difficult to reproduce or reconcile with the simplest version of the model. Current evidence therefore supports a quantum-influenced chemical compass while also showing that the mechanism is more complicated than one protein acting as a perfect built-in compass needle. Birds may also possess more than one magnetic sense. The eye-based system is often proposed to provide compass direction, while iron-containing structures could help detect field strength or local magnetic variations used as part of a positional map. A 2026 study of homing pigeons reported superparamagnetic macrophages in the liver and found that temporarily depleting these cells disrupted orientation during overcast flights while leaving navigation, under a visible sun largely intact. The researchers proposed that these magnetic cells contribute to pigeon navigation, although the finding is new, species-specific, and does not by itself replace the cryptochrome hypothesis developed largely from experiments on migratory songbirds. The emerging picture is therefore not of one universal compass hidden in every bird, but of several sensory systems cooperating with memory, smell, celestial cues, polarized light, and familiar landscapes. A young migrant may inherit a general direction and distance for its first journey, then refine later routes by learning the geography of coastlines, winds, stars, and magnetic conditions. Earth's field is useful because it remains present at night and behind clouds, but it is not perfectly stable. Solar activity can disturb it, metal structures can distort it locally, and magnetic intensity and inclination change gradually across the planet. A bird's nervous system must combine this uncertain signal with other information rather than obeying it blindly. The quantum compass is remarkable precisely because it operates within a warm, wet, noisy body, an environment that seems hostile to delicate quantum behavior. Yet the relevant electron states need survive only for an extremely brief time before chemistry transforms their tiny differences into larger biological effects. Evolution would not need to preserve a fragile quantum state for seconds or minutes. It would only need to build a molecular reaction fast and sensitive enough to convert the field's direction into a reliable bias repeated across many molecules. Your own vision begins with similarly microscopic events, when individual photons change the shapes of proteins in your retina, and those molecular changes eventually become a world of color and form. Birds may have extended that ancient partnership between light and chemistry, using the same sensory surface to detect an invisible feature of the planet itself. Whether they experience it as a visible pattern, a directional feeling, or something with no human equivalent remains unknown. But each time a small bird leaves familiar ground and continues through a moonless night, it may be reading a layer of Earth that surrounds you just as completely, while remaining absent from your conscious world. The field passes through both of you, yet only one nervous system may turn its silent geometry into a direction home. The memory rewrite effect. Why remembering something quietly changes it. Every time you open an old memory, you may return it to storage carrying small changes that were not there before. The event itself remains in the past, but your access to it is rebuilt in the present from fragments of sensory detail, emotion, meaning, and knowledge acquired afterward. Your brain does not preserve most experiences as complete films waiting to be replayed. Instead, a cue, a smell, a photograph, a familiar voice reactivates parts of a distributed neural pattern, and the mind reconstructs a coherent scene from whatever information is available. This is why remembering can feel vivid while still being incomplete. The empty spaces are filled so smoothly that you rarely notice where direct recollection ends and inference begins. During retrieval, some memories can enter a temporary state of increased flexibility before they become stable again, a process researchers call reconsolidation. In this window, new information may sometimes be integrated into the reactivated memory. Its emotional strength may shift, or certain details may become easier or harder to recover later. Human experiments have shown that reactivating an established memory before introducing new learning can alter later recall. Although the effect depends on conditions such as the age and strength of the memory, the kind of reminder used, and whether the new event creates enough surprise to signal that the old knowledge needs updating. Reconsolidation is therefore a real and important research framework, but it is not a universal editing command. Some major human findings have been difficult to reproduce, and scientists still debate when an altered response reflects genuine modification of an old memory rather than the creation of a competing new one. The brain's willingness to update memory is not simply a weakness. A perfectly fixed memory system would preserve obsolete information even after the world changed. If a place once contained danger but later became safe, or if a familiar person began behaving differently, survival would require the old representation to absorb new evidence. Remembering allows the past to remain useful by adjusting it to the present. The cost of that flexibility is distortion. In classic misinformation experiments, people who witness an event and later encounter misleading descriptions may eventually report details that were never present. A suggestive question can introduce a new object, alter the apparent speed of a vehicle, or change how a person interprets what they saw. The false detail does not always feel like an external suggestion. It may become woven into the remembered scene and later arrive with the familiarity of genuine experience. Social influence can deepen the effect. Experiments have found that hearing other people confidently recall inaccurate details can produce persistent errors in one's own memory, accompanied by changes in brain activity associated with memory representation, rather than simple public agreement. The problem is often one of source monitoring. You may remember the detail but lose reliable access to where it came from. Was the broken window visible in the original scene, mentioned later in conversation, suggested by a question, or created while you pictured what probably happened? As the source fades, the detail can remain. Repetition makes this more dangerous because familiarity is easily mistaken for truth. Each retelling also encourages compression. Details that support the story are rehearsed, while awkward or irrelevant pieces receive less attention and become harder to retrieve. Research on retrieval-induced forgetting shows that repeatedly recalling selected information can reduce later access to related information that was not practiced, as the brain suppresses competing material to reach the desired answer more efficiently. In this way, remembering one version of an experience can quietly make alternative details less available. Family stories provide a familiar example. A childhood event may be retold so often that the polished family narrative becomes easier to recall than the original experience. Eventually, you may remember the story of the moment more clearly than the moment itself. Photographs can have a similar effect. They preserve real visual information, yet repeated viewing may cause your memory to gather around the camera's narrow perspective, replacing details that once existed outside the frame. Emotion adds another layer. Highly emotional memories often feel exceptionally clear because the mind preserves their importance and repeatedly rehearses them, but confidence and vividness do not guarantee exact accuracy. Central features may remain strong while timing, sequence, peripheral details, and later interpretations drift. This explains why two honest people can remember the same argument differently without either one deliberately lying. Each person attended to different signals, interpreted them through different expectations, revisited the event in different emotional states, and strengthened different parts through later reflection. A memory is shaped not only by what happened, but by what the event later came to mean. This has serious consequences for eyewitness testimony, therapy, personal conflict, and identity. Aggressive or leading questioning can contaminate recall, while repeated demands for certainty may encourage a person to fill uncertainty with plausible detail. At the same time, the flexibility of memory may offer therapeutic possibilities. Carefully recalling a distressing experience in a safe setting can sometimes help reduce its emotional power or attach new meaning to it. But this does not erase the historical event, and reconsolidation-based treatments remain more limited and condition-dependent than popular claims often suggest. The goal is usually not to delete memory, but to change the fear, expectation, or automatic response connected to it. Your memories are therefore neither perfect recordings nor meaningless inventions. They are adaptive constructions constrained by real traces of experience, but continually influenced by attention, context, later knowledge, and the act of retrieval itself. This means remembering is never completely passive. Each return is also a new encounter between the person who lived the event and the person you have since become. The past cannot be reopened in its original form because you do not approach it with the same brain, the same expectations, or the same understanding. What survives is a living version, stable enough to guide you, yet flexible enough to change. And perhaps the most unsettling lesson is not that your memories are untrustworthy, but that the story you use to recognize yourself is being revised in small, silent ways each time you ask it to speak. The deep Earth biosphere, life existing kilometers beneath the surface. Far below every forest, city, and ocean floor, life continues in places where a year may be too brief to measure meaningful change. This hidden realm is called the deep biosphere, a collection of microbial ecosystems living inside water-filled fractures, buried sediments, coal beds, and pores within solid rock, sometimes several kilometers beneath Earth's surface. There is no sunlight there, almost no fresh organic material, and often very little space, yet bacteria, archaea, fungi, and even a few microscopic animals have been recovered from environments once assumed to be biologically empty. Scientists have found diverse microbial communities in crystalline rock more than 2 kilometers below Finland, cultivated microorganisms from ancient coal-bearing sediments roughly 2 kilometers beneath the seafloor, and studied fracture waters reach through South African mines extending beyond 4 kilometers underground. These discoveries do not mean the crust is densely packed with creatures. Deep life is usually sparse, unevenly distributed, and concentrated wherever liquid water, usable chemistry, and tolerable temperatures meet. A single fracture containing ancient groundwater may support an ecosystem, while nearby dry rock remains almost sterile. Without photosynthesis, many organisms survive by exploiting chemical reactions between water and minerals. Some consume hydrogen produced when rock reacts with water. Others use methane, sulfate, iron, or small carbon compounds released from buried material. Natural radioactive decay can split water molecules through radiolysis, generating hydrogen and oxidizing chemicals that provide a slow but continuous source of biological energy. In old marine sediments, this process may become especially important after most surface-derived food has been consumed, allowing life to persist on energy produced inside the sediment itself. The pace of existence under these conditions can be extraordinarily slow. Near the surface, a bacterium may divide within hours, but some deeply buried cells appear to maintain themselves for years, decades, or potentially much longer before reproducing. Much of their energy may be spent not on growth, but on repairing damaged molecules, maintaining cell membranes, and preserving the basic chemical differences that keep a cell alive. They may exist close to the minimum energy required for biological survival, occupying a state somewhere between active growth and complete dormancy. This makes the deep biosphere difficult to study because detecting DNA does not automatically prove that an organism is alive, and measuring extremely faint activity can be confused by contamination introduced during drilling. Researchers sterilize equipment, track substances added to drilling fluids, compare samples from different depths, and use chemical and genetic evidence together to determine whether microbes truly originated underground. The organisms themselves can also be difficult to grow in laboratories because a species adapted to high pressure, darkness, unusual minerals, and an extremely limited food supply may not respond to the rich nutrients normally used to culture microbes. When researchers successfully cultivated communities from 2 kilometer deep coal and shale beds, the experiments continued for years, revealing how poorly ordinary laboratory timescales match life in the subsurface. These ecosystems are not isolated curiosities. Deep microbes influence the movement of carbon, sulfur, nitrogen, hydrogen, and metals through Earth's crust. They can produce or consume methane, transform minerals, alter groundwater chemistry, contribute to corrosion, and leave chemical signatures that remain in rock long after the organisms disappear. Research indicates that subsea floor communities affect major biogeochemical cycles and aspects of ocean chemistry, even though their individual reactions may proceed almost invisibly. The true size of this biosphere remains uncertain because most of the crust has never been sampled, and estimates of its biomass have changed as scientists improved their methods. What is clear is that the habitable part of Earth extends far beyond the thin green surface visible from space. The lower limit is not a fixed depth, but a shifting boundary controlled by heat, water, pressure, salinity, rock permeability, and available energy. As depth increases, temperature eventually becomes too high for known life, but that point lies deeper in cold crust and shallower in geologically hot regions. The existence of these communities also changes the search for life elsewhere. A planet with a frozen, irradiated, or barren surface might still provide protected fractures where water and rock generate chemical energy below ground. Earth's deep biosphere shows that a living world does not have to advertise itself with forests, oxygen, or sunlight. It may survive as scattered cells moving through cycles so slowly that an entire human civilization would pass like a brief disturbance above them. You spend your life thinking of the ground as the boundary beneath the living world, yet for countless organisms, it is the entrance. Below your feet, life becomes quieter, slower, and increasingly difficult to distinguish from geology itself, raising a final question. If an organism can remain hidden in stone for thousands of years while consuming almost nothing, how little must life do before you stop calling it alive? The secret clock inside every organ. Why your body does not experience one single time. At midnight, your brain, liver, heart, kidneys, muscles, and immune cells may all belong to the same body while behaving as though they are standing in slightly different hours. You do not contain one biological clock, but a coordinated network of clocks, distributed through nearly every organ and many individual cells. The best-known timekeeper sits in a small region of the brain called the suprachiasmatic nucleus, positioned where it can receive information about light from the eyes. Morning light adjusts this central clock to the outside world, helping organize sleep, alertness, body temperature, hormone release, and many other daily rhythms. Yet the brain does not personally control every timed event like a conductor dictating each note. The liver, pancreas, heart, lungs, kidneys, muscles, fat tissue, digestive system, and immune cells contain their own molecular oscillators. Inside these cells, groups of clock genes and proteins activate and suppress one another in repeating cycles that take approximately a day to complete. This biological machinery allows an organ to prepare for predictable demands before they arrive, rather than merely reacting afterward. Your digestive system can become ready for food. The liver can adjust how it stores and releases energy, and the cardiovascular system can alter blood pressure and heart activity according to the expected period of rest or movement. These clocks are related, but their schedules are not identical because each tissue performs a different task. The body is less like a room containing one ticking clock, and more like a city whose hospitals, power stations, transport systems, kitchens, and waste facilities follow separate timetables while attempting to serve the same population. Light is the strongest signal for the brain's central pacemaker, but peripheral organs also listen closely to meals, physical activity, hormones, nervous system signals, and daily changes in body temperature. This creates an important difference between the time shown by the sky and the time expected by your metabolism. When you eat, nutrients and metabolic hormones tell the liver and other tissues that an active feeding period has begun. If meals occur at a consistent time, these signals help peripheral clocks remain aligned with one another. When eating shifts to an unusual hour, the liver may begin adjusting to the new food schedule, even while the brain remains tied to the light-dark cycle. Studies show that peripheral tissues respond differently to feeding rhythms, with the liver being especially sensitive to meal timing, while the central brain clock is more resistant because it remains strongly synchronized by light. Your organs can therefore become temporarily desynchronized, The brain may be signaling biological night while the stomach, pancreas, and liver are being asked to process a large meal as though daytime activity has begun. This internal disagreement is one reason jet lag and shift work can affect more than sleep. After crossing time zones, your eyes immediately receive light from the new location. But the many clocks throughout the body do not all reset at the same speed. Hunger may arrive at an inconvenient hour. Digestion may feel altered. Alertness may rise when you want to rest. And body temperature may follow the rhythm of the place you recently left. The discomfort is not simply confusion in your thoughts. It reflects an entire clock network slowly negotiating a new shared schedule. Repeated misalignment has been associated with metabolic and cardiovascular problems, although risk depends on many factors and does not mean that one late night directly causes disease. Each organ also uses time to separate tasks that would interfere with one another if performed at full strength simultaneously. The liver changes the activity of enzymes involved in glucose, fats, cholesterol, detoxification, and drug processing across the day. Skeletal muscle adjusts energy use, repair, and physical performance according to both its local clock and signals from the brain. Research in animals has shown that communication between central and muscle clocks helps preserve daily muscle function, revealing that healthy timing depends not only on each clock running, but on different tissues exchanging temporal information. The immune system also follows rhythms. The movement and activity of immune cells, inflammatory signaling, and responses to infection can vary with biological time because defense must be balanced against repair and energy use. Hormones act as traveling time signals, reaching many tissues through the blood and adjusting local rhythms without forcing every organ into an identical phase. Some hormones provide strong resetting cues, while others fine-tune the processes controlled by a tissue clock. This means that body time is not a single number. One organ may be approaching a peak in activity, while another is entering a quieter phase. The differences are purposeful. Your kidneys do not need to perform exactly like your muscles, and your liver does not require the same timetable as your brain. Coordination does not mean uniformity. It means that distinct rhythms meet at the correct moments. The medical implications are beginning to attract serious attention. If the activity of an enzyme, receptor, immune pathway, or detoxification system changes during the day, then the same dose of a medicine may be absorbed, processed, or tolerated differently depending on when it is taken. This idea, known broadly as chronotherapy, is already relevant to certain established treatments and is being investigated in cardiovascular care, cancer therapy, inflammatory disease, and other fields. But there is no universal best time for every drug, and treatment schedules should not be changed without clinical guidance, because the relevant rhythm depends on the medication, illness, individual, and available evidence. The deeper discovery is that your organs are not merely passive machines waiting for commands. They anticipate. A liver cell can prepare for nutrients that usually arrive later. A muscle can shift its molecular priorities before the expected active period. A kidney can organize filtration and salt handling around recurring demands. These rhythms continue for a time, even when external cues are removed, showing that they are generated internally, although they gradually drift unless light, food, activity, and other signals reset them. You experience yourself as one continuous being because consciousness gathers the body's many processes into a single life. Beneath that unity, however, time is being interpreted locally. Your eyes report the hour of the world. Your stomach reports the hour of eating. Your muscles report the hour of movement. And your cells compare those signals with cycles inherited from countless generations that lived beneath predictable days and nights. Health depends partly on their ability to disagree slightly without losing contact, like musicians playing different parts of the same composition. When the relationship holds, you rarely notice the machinery. When it breaks, the body reveals that sleep, hunger, energy, temperature, digestion, and alertness were never controlled by one hand on one clock face. You do not move through each day as a single timer counting forward. You move as a community of living rhythms, each organ carrying its own version of the hour and continually asking the others whether it is still time to work, to repair, to eat, or finally to become quiet. When space behaves like a fluid, theories that turn the cosmos into a moving ocean. Empty space may look perfectly still, yet a spinning planet can twist it. A colliding pair of black holes can send waves through it, and some theories suggest that the smooth cosmos around you could be the large-scale behavior of something far deeper. This does not mean space is literally filled with water, air, or an invisible substance flowing past Earth. In Einstein's general relativity, space-time is not a passive container in which events occur. Its geometry can bend, stretch, and evolve in response to matter and energy. The fluid comparison becomes useful because many of these changes resemble familiar motions in an ocean. A heavy object placed in water reshapes the surface around it, while a massive body alters the geometry through which nearby objects move. A whirlpool carries floating objects around its center, while a rotating planet or star produces frame dragging, a subtle effect in which the rotation of matter influences nearby inertial motion. Gravity Probe B measured this tiny twisting around Earth by tracking the changing orientation of extremely precise gyroscopes in orbit, confirming that rotation affects the surrounding space-time in the way relativity predicts. The effect is far stronger near rapidly rotating black holes, where matter and light can be forced to move with the rotation within a region outside the event horizon. Yet nothing there is being carried by a material current. What appears to flow is the geometry defining which paths through space and time are physically possible. Space-time can also support traveling disturbances. When massive objects accelerate asymmetrically, they can create gravitational waves that spread outward, alternately stretching distances in one direction and compressing them in another. LIGO detects these waves from violent events such as merging black holes and neutron stars, showing that the geometry of the universe can carry energy through rhythmic distortions without needing a physical medium like water or air. The old idea of a luminiferous ether imagines space as a hidden substance providing a preferred state of rest for light. But modern relativity does not require such a background. The fluid language is therefore an analogy, not a return to the discarded belief that planets move through a detectable cosmic liquid. Still, the analogy becomes surprisingly exact in certain laboratory systems. In 1981, physicist William Unruh showed that sound waves traveling through a moving fluid can obey equations similar to those describing fields near a black hole. If the fluid crosses a boundary where it moves faster than sound can travel against the current, sound produced on the downstream side cannot escape upstream. This creates an acoustic horizon, a laboratory counterpart to the boundary of a black hole. Researchers have since built analog horizons using flowing water, ultra-cold atomic gases, and other materials, studying wave scattering and back reaction under controlled conditions. These experiments do not manufacture real gravitational black holes, and they do not prove that space-time is made of fluid. They reveal that very different physical systems can share the same deeper mathematical structure. A ripple approaching a fast current can behave like radiation near a horizon, because both are governed by relationships between waves, flow, and the maximum speed at which information can move through the system. This raises an extraordinary possibility. Perhaps some features of gravity are not unique to a fundamental fabric called space-time, but belong to a broader class of collective systems. Temperature offers a useful comparison. A single molecule does not possess temperature in the ordinary sense. Temperature emerges only when enormous numbers of particles are considered together. Sound behaves similarly. No individual atom contains a sound wave, yet coordinated motion across many atoms produces one. Some approaches to quantum gravity ask whether space itself may work this way. Perhaps smooth distance, curvature, and even the flow of time are collective properties emerging from microscopic ingredients that are not spatial in the familiar sense. In group field theory, for example, researchers explore models in which a macroscopic universe emerges from large numbers of quantum building blocks, forming condensate-like states. allowing cosmological behavior to be treated somewhat like the hydrodynamics of an underlying quantum system. This remains a theoretical research program rather than an experimentally confirmed description of reality, but it offers a concrete example of how continuous spacetime might arise from more fundamental entities, just as fluid motion arises from atoms too small to see individually. Other proposals go further and describe the vacuum as something resembling a quantum superfluid. In an ordinary superfluid, particles move collectively with unusual coherence and can flow without the ordinary resistance of a classical liquid. A hypothetical superfluid vacuum could allow familiar particles and forces to appear as excitations moving through a deeper quantum state. In such a picture, what you call empty space would be closer to the calm surface of an unseen ocean, while matter might resemble stable patterns, vortices, or waves within it. These models are speculative, however, and no observation has established that the physical vacuum is a literal superfluid. They must reproduce the extraordinary precision of relativity, explain why no preferred cosmic rest frame is observed, and produce testable predictions that distinguish them from existing physics. Without such evidence, the ocean remains a theoretical possibility rather than a discovered substance. The more conservative and experimentally secure statement is that the universe can often be described using fluid concepts even when space-time itself is not a fluid. Cosmologists treat large populations of matter and radiation as effective fluids because tracking every particle individually would be impossible. Stars, gas, radiation, and other components can be averaged into densities and pressures that evolve as the universe expands. This approach describes the collective behavior of cosmic contents, not a stream of space pouring through the galaxies. The distinction matters because metaphors can easily become false pictures. Expansion does not mean the universe is flowing outward into a larger emptiness, and gravitational waves are not surface waves traveling across a hidden cosmic sea. Yet the similarities continue to teach physicists something valuable. They show that horizons, waves, turbulence-like behavior, and collective order can emerge in systems whose microscopic ingredients are completely different. A whirlpool in a tank may help illuminate the behavior of fields near an object millions of times more massive than the sun. A cloud of ultra-cold atoms may imitate a boundary from which sound cannot return. A theory built from quantum fragments may produce equations resembling the expansion of an entire universe. The cosmos does not need to be made of liquid for fluid thinking to reveal its structure. What matters is that both fluids and space-time can distribute influence across a system, carry disturbances, form boundaries, and develop large-scale behavior that cannot be understood by staring at one isolated point. You experience space as emptiness because nothing pushes against your body when you move. But physics describes that emptiness as capable of curvature, oscillation, rotation, and perhaps emergence from an unseen microscopic order. The ocean image is therefore neither fully true nor entirely wrong. It is a bridge between what your senses understand and what equations reveal. A way of seeing the universe not as a rigid stage, but as something active, responsive, and capable of changing shape. And if space-time is eventually shown to be an emergent collective state, then the quiet space surrounding you may be like the surface of a deep sea, smooth at your scale. While beneath that smoothness, an unknown world of quantum motion creates the very distances through which you believe you are moving. The universe's oldest light, a glow that has traveled since before galaxies existed. Aim a sensitive microwave receiver at the darkest patch of sky you can find, far from every visible star and galaxy, and a faint ancient glow will still be waiting there. This radiation is the cosmic microwave background, the oldest light humans can directly observe, and one of the closest things nature has given us to a photograph of the infant universe. It did not come from the first stars, because no stars existed when this light began traveling freely. It was released roughly 380,000 years after the beginning of cosmic expansion, during an age when the universe looked nothing like the transparent darkness surrounding galaxies today. Earlier than that, space was filled with a hot, dense plasma of free electrons and atomic nuclei. Photons could not travel far without colliding with charged particles, so the young cosmos was opaque, more like the glowing interior of a cloud than an open night sky. As expansion continued, the universe cooled enough for electrons to join nuclei and form neutral atoms, mostly hydrogen and helium. Once most free electrons were removed from the plasma, light could finally cross great distances without being scattered again and again. Those liberated photons have been traveling ever since, passing through the formation of the first stars, the growth of galaxies, and nearly the entire history of the cosmos before reaching instruments near Earth. Expansion stretched their wavelengths during the journey, reducing what was once an intense thermal glow into microwaves with an average temperature of about 2.7 degrees above absolute zero. The light has not become tired in the ordinary sense. The space through which it traveled expanded, lengthening the waves along with it. The cosmic microwave background arrives from every direction, but this does not place Earth at a special center. Wherever an observer exists, they receive ancient photons from a surrounding shell, representing the distance light has traveled since the universe became transparent. Looking farther in any direction means looking further back in time, until every line of sight eventually reaches this glowing boundary. The familiar oval images of the background are not pictures of an object floating beyond the galaxies. They are maps of the entire sky flattened onto a page, much as a map of Earth turns a sphere into an oval. The colors are also greatly exaggerated. The true background is almost perfectly uniform, with temperature differences of only about 1 part in 100,000. Yet those tiny variations are among the most important irregularities ever measured. Slightly warmer and cooler regions correspond to small differences in density in the early universe. Areas containing a little more matter exerted slightly stronger gravity, drawing in additional material over immense spans of time. Those nearly invisible differences became the starting conditions from which stars, galaxies, clusters, and the largest cosmic structures eventually developed. The night sky therefore owes its complexity to imperfections so small that without precise instruments, the infant universe would appear completely smooth. The pattern also preserves the imprint of sound waves that once moved through the early plasma. Gravity pulled material toward denser regions, while the pressure of trapped radiation pushed outward, creating cycles of compression and expansion. When atoms formed and light escaped, those oscillations were suddenly preserved in the distribution of matter and radiation. Like ripples frozen at the moment a pond became solid. Astronomers study the sizes and strengths of these patterns to learn about the contents, geometry, age, and early expansion of the universe. They can estimate how much ordinary matter existed, how strongly unseen mass influenced the plasma, and whether space is curved on the largest scales. The result is remarkable. A glow so cold that your body radiates far more strongly than it does, yet detailed enough to function as a record of conditions billions of years before Earth formed. Detecting that record required separating it from everything closer and brighter. The Milky Way produces microwave emissions through dust, hot gas, and energetic charged particles, while radio sources and instrument noise add further contamination. Satellites observe the sky at several frequencies because foreground materials have different spectral signatures from the ancient background. By comparing those frequencies, researchers can remove much of the local emission and uncover the underlying cosmic pattern. NASA's COBE mission showed that the background has an extraordinarily precise thermal spectrum and made the first detection of its minute temperature variations. WMAP later produced sharper full-sky maps, and ESA's Planck spacecraft measured temperature and polarization patterns with greater precision. These missions did not merely take clearer versions of the same picture. Each allowed physicists to test whether a simple model of cosmic history could explain the pattern at many different scales. The light also carries polarization, a preferred orientation produced when photons scattered in particular environments before escaping. Different polarization patterns reveal information not contained in temperature alone. Some preserve the influence of early density variations, while researchers continue searching for subtler patterns that could contain traces of processes from a far earlier period of rapid expansion. No confirmed observation has yet revealed the specific primordial gravitational wave signature often associated with inflation, so this remains a major scientific goal rather than an established discovery. It is equally important to understand what the cosmic background does not show. It is not light from the exact beginning, and it does not allow an ordinary telescope to see the earliest 380,000 years directly. Photons existed during that hidden era, but the plasma continually scattered them and erased any straightforward image they might have carried. The background instead shows the moment when the curtain lifted. It records a universe already hundreds of thousands of years old, yet still without planets, stars, galaxies, or the heavy elements from which living bodies would later be built. Everything you recognize in the sky developed after this light began its journey. When one of these microwave photons finally enters a detector, it completes a passage that started before the first sunrise anywhere in existence. It has crossed a changing universe while preserving a small piece of the conditions from which that universe grew. And hidden within that nearly uniform glow is a quiet lesson about beginnings. The structures that appear permanent today were once only faint differences in temperature, barely distinguishable from one another, waiting for gravity and time to turn tiny variations into a cosmos capable of looking back at its own first visible light. The universe before stars. What existed during the first cosmic darkness. For a long interval after the young universe became transparent, there was nowhere in existence where a sunrise could happen. No stars burned, no galaxies shone, no planets reflected light, and none of the heavier elements needed for rock, oceans, or living cells had yet been created. Astronomers call this period the cosmic dark ages, but the darkness was not emptiness. Space was filled mainly with neutral hydrogen and helium, along with invisible matter whose gravity was already beginning to shape the future. The gas was thin, cold, and spread across an expanding universe, while small differences in density slowly grew under gravity. Regions containing slightly more matter attracted more material, deepening into gravitational basins. Invisible matter played a central role because it could begin gathering without needing to cool or radiate energy. Ordinary gas followed into these growing concentrations, but it could not immediately become a star. Before a cloud can collapse into a compact object, it must lose heat. Otherwise, internal pressure resists gravity and keeps the cloud swollen. In the modern universe, atoms of many elements, molecules, and dust grains help gas release energy efficiently. During the Dark Ages, none of that chemical richness existed. The universe contained almost nothing heavier than lithium in trace quantities. So the first collapsing clouds had to depend mainly on simple molecular hydrogen, formed slowly through reactions in the primordial gas. Even a small amount could radiate enough heat away to let certain clouds continue shrinking. Inside the earliest small gravitational halos, gas collected, cooled, and became denser until gravity finally overwhelmed its resistance. These were not yet galaxies in the familiar sense, but the hidden foundations from which the first luminous objects would emerge. The first stars, usually called population 3 stars, were born from this chemically simple material. No such star has been directly identified, so their properties are reconstructed through simulations, nuclear physics, and the chemical fingerprints they may have left in later stars. Many models suggest that the lack of efficient cooling allowed large amounts of gas to collect before collapsing, producing stars that were often more massive than the Sun, although the first stellar population may have included a wider range of masses than the simplest early models predicted. Their lives could have been brief and violent. Massive stars consume nuclear fuel quickly, and some may have ended as powerful supernovae, while others may have collapsed into black holes with less visible explosion. In their interiors, the first substantial supplies of carbon, oxygen, silicon, iron, and other heavier elements were created. When some of these stars died, they released those elements into surrounding space, changing what future clouds were capable of becoming. The next generations of stars no longer formed from pristine hydrogen and helium alone. Their gas could cool more efficiently, fragment into smaller clumps, and eventually build longer-lived stars, rocky worlds, and the chemical ingredients that would appear much later in biology. The first light, therefore, did more than illuminate darkness. It altered the material possibilities of the universe, yet it also began destroying the quiet conditions from which it emerged. Ultraviolet radiation from early stars and galaxies stripped electrons from neutral hydrogen, gradually transforming the intergalactic gas during the era known as ionization. This process did not occur everywhere at once. Bright sources created expanding ionized regions around themselves, and those regions grew and overlapped until much of the gas between galaxies had been changed. The universe moved from darkness into a patchwork dawn, with islands of light surrounded by enormous regions that remained neutral and unseen. Ordinary telescopes cannot simply photograph most of the true dark ages because there were no stars to provide visible or infrared light. Instead, scientists hoped to study the era through neutral hydrogen itself. Hydrogen atoms can emit or absorb radio waves at a characteristic wavelength of 21 centimeters. As the universe expands, signals produced in the dark ages are stretched to far longer radio wavelengths before reaching the present. Their strength and distribution could reveal how cold the gas became, how early density structures grew, whether unexpected heating occurred, and whether invisible matter behaved exactly as current models predict. Unlike a photograph showing isolated objects, a detailed map of this hydrogen signal could provide a three-dimensional record of enormous volumes of the young universe before astrophysical activity made conditions more complicated. It might reveal the first clouds approaching collapse and show how the earliest stars began changing the gas around them. For this reason, the Dark Ages are sometimes described as unusually clean territory for testing fundamental cosmology. The ingredients were fewer, the physics was simpler, and the later confusion of mature galaxies had not yet appeared. Detecting this signal is exceptionally difficult. Human radio transmissions, natural emissions from our galaxy, and disturbances caused by Earth's ionosphere can overwhelm the ancient hydrogen signature by many orders of magnitude. Some of the lowest frequencies may be nearly impossible to measure accurately from the ground, which is why scientists have proposed radio observatories on the far side of the Moon. There, the Moon itself could block much of Earth's radio noise, and the absence of a terrestrial ionosphere would allow instruments to listen to frequencies that are distorted or absorbed above our planet. Such observatories remain proposals rather than completed windows into the Dark Ages, and no detailed map of this era has yet been obtained. What existed before the stars, then, was not a dead universe waiting passively for light. It was a universe performing quiet construction without any visible witness. Gravity was gathering material into the first hidden structures. Primordial gas was slowly discovering pathways to cool. Invisible halos were becoming nurseries for objects that had never existed before. The chemistry was simple, but its consequences were immense. Every later galaxy, every rocky planet, and every atom in your body heavier than hydrogen ultimately depends on the transformation that began when the first clouds finally became dense and cold enough to ignite. The cosmic darkness was not an absence of history. It was the period in which history was being prepared without illumination. And perhaps that is what makes this forgotten age so difficult to picture. The universe was already becoming everything you know, but almost none of it had yet learned how to shine. The strange stability of matter. Why atoms do not collapse into themselves. Every atom in your body is held together by an attraction that seems, at first, as though it should destroy it. The negatively charged electrons are drawn toward the positively charged nucleus. So a simple classical picture appears to predict disaster. If an electron were a tiny planet circling the nucleus, it would be an accelerating electric charge. It would radiate energy, lose speed, spiral inward, and collapse into the center in an extremely short time. matter would have no lasting size, chemistry would never begin, and the objects around you could not exist in their familiar form. The reason this does not happen is that an atom is not a miniature solar system. An electron inside an atom does not travel along one definite circular road, and the fuzzy shapes drawn around nuclei are not blurry versions of hidden planetary orbits. They represent quantum states, stable patterns describing where an electron may be detected and how its energy is distributed. In the lowest energy state of an atom, the electron is not continuously losing energy because it is not behaving like a classical charge bead racing around the nucleus. It occupies a stationary quantum state whose measurable probability pattern remains unchanged with time. Light is emitted or absorbed mainly when the atom moves between allowed energy states, not simply because an electron exists near a nucleus. The atom therefore stops at a lowest permitted energy rather than descending forever. This lowest state has a finite size, and the reason it cannot shrink without limit reveals one of the deepest balancing acts in nature. Pulling the electron closer to the nucleus lowers its electrical potential energy, so attraction encourages contraction. But confining the electron to an increasingly tiny region makes its momentum less definite and raises the kinetic energy associated with that confinement. The uncertainty principle is often described as a limitation on what an observer can know, but here it is more fundamental than imperfect measurement. It expresses how quantum states are structured. A state made extremely narrow in position must contain a broad range of momenta. Forcing the electron into a smaller and smaller space would therefore make the energy climb sharply. The uncertainty principle is not a mysterious outward force pushing the electron away. Rather, it prevents the lowest energy state from being one in which both position and motion are arbitrarily compressed. The atom settles at the scale where the reduction in electrical energy and the increase in confinement energy reach a stable compromise. That balance gives hydrogen its characteristic size and ensures that the electron's probability cloud spreads around the nucleus instead of collapsing into a point. This does not mean the electron avoids the nucleus completely. In some atomic states, including the ground state of hydrogen, there is a non-zero probability of detecting the electron within the tiny volume occupied by the nucleus. But briefly being found there is not the same as permanently falling in and remaining there. A localized electron at the center would not automatically represent a lower energy atomic state. Nature selects allowed states according to the complete quantum system, not according to the classical idea that closer must always mean more stable. The nucleus is also not an infinitely small electrical point. It has a finite size and contains protons and neutrons bound mainly by the strong nuclear interaction. Protons electrically repel one another, but at nuclear distances, the strong force can overcome that repulsion and hold many nuclei together. This stability has limits. Some combinations of protons and neutrons are unstable and undergo radioactive decay, showing that nature does not make every possible nucleus permanent. Even stable atoms are therefore not frozen objects. Their electrons possess quantum energy, their nuclei can vibrate, and the surrounding electromagnetic field is never equivalent to absolute stillness. Stability means that the system remains in a persistent state unless energy or another interaction changes it. It does not mean that every component is motionless. The puzzle becomes even deeper when you move from a single hydrogen atom to an object containing an enormous number of electrons. The uncertainty principle helps keep an individual atom from collapsing, but by itself, it does not fully explain why a stone, a table, or your body has a sensible volume that grows with the amount of matter present. For that, another quantum rule becomes essential: the Pauli exclusion principle. Electrons belong to a class of particles called fermions, and identical fermions cannot all occupy the same quantum state. In an atom with many electrons, only a limited number can remain in the lowest available state. Additional electrons must occupy different states, often extending farther from the nucleus and possessing different energies and spatial patterns. This produces the layered organization commonly described as electron shells and provides the foundation for the periodic table. Carbon behaves differently from oxygen Sodium reacts differently from neon, and chemical bonds take their particular forms largely because electrons fill the available quantum states according to this rule. The exclusion principle is not an ordinary repulsive force between electrons. Two electrons can be close together under appropriate conditions, especially if their internal spin states differ. What the principle forbids is a complete duplication of the same quantum state by identical electrons. That abstract restriction has a physical consequence. When matter is compressed and electrons are forced into a smaller region, they must spread into a larger range of available momentum states, raising the system's energy and resisting further compression. Rigorous studies of the stability of matter show that the uncertainty principle helps stabilize individual atoms, while the exclusion principle is crucial for the stability and sensible scaling of ordinary matter in bulk. Without exclusion, adding more charged particles could make matter bind increasingly strongly and occupy disproportionately less space, instead of forming stable objects whose volume roughly grows with particle number. What you experience as the solidity of an object is therefore not mainly the result of tiny, hard spheres touching. Most of an atom's volume is described by its electron cloud, while the nucleus occupies only a minute central region. When your hand presses against a table, the electron distributions in your skin interact electromagnetically with those in the table, and the quantum restrictions on rearranging identical electrons make strong overlap energetically costly. The surface feels impenetrable because the combined system resists being forced into forbidden or high-energy configurations, not because atomic particles possess perfectly rigid outer shells. Under normal conditions, this resistance is extraordinarily effective, but it is not absolute. In the core of a white dwarf, gravity compresses matter so intensely that ordinary atoms can no longer retain their familiar structure, and electrons form a highly compressed quantum system whose exclusion-based pressure helps support the star. Under still more extreme conditions, electrons can combine with protons through the weak interaction, contributing to matter dominated by neutrons. This does not contradict atomic stability. It shows the range within which that stability operates. The atoms around you persist because everyday pressures and temperatures are nowhere near sufficient to overcome the quantum energy structure that protects them. Even electron capture, a real form of radioactive decay in certain nuclei, should not be mistaken for the classical collapse of an orbiting electron. It occurs only when the nuclear composition permits a weak interaction transformation and when the total energy conditions allow it. An ordinary hydrogen atom cannot simply lower its energy forever by allowing its electron to disappear into the proton. Matter's stability is therefore not produced by one protective barrier, but by several laws working together. Electrical attraction binds electrons to nuclei. Quantum confinement prevents unlimited shrinking. Discrete energy states provide a lowest level. The exclusion principle organizes many electrons and resists bulk compression. And nuclear forces preserve many atomic nuclei. Remove any major part of this structure and the material world would be radically different. The most familiar objects in your life are stable because nature does not permit their particles to choose every arrangement that classical intuition can picture. A cup remains on a table, your bones retain their shape, and the air does not collapse into a featureless point because matter is built from restrictions as much as from forces. What appears to you as stillness is an enduring quantum compromise. Attraction is allowed to gather particles together, but the architecture of their possible states prevents that gathering from continuing without end. And perhaps this is the strangest lesson hidden inside an ordinary atom. The universe creates durable form, not by eliminating opposing tendencies, but by balancing them so precisely that a structure made from restless quantum possibilities can remain stable long enough to become stars, planets, cells, memories, and the hand with which you reach out to touch the world, the invisible rain passing through your body, cosmic particles arriving every second. Before you finish this sentence, several particles created in violent collisions high above Earth will have passed through your body without producing any sensation at all. They arrive continuously from the sky, crossing roofs, clothing, skin, and sometimes meters of rock before disappearing or decaying. We often call this invisible rain cosmic rays, but the name is slightly misleading because most cosmic rays are not rays of light. They are fast-moving charged particles, mainly protons and the nuclei of atoms, traveling through space with energies that can greatly exceed anything found in ordinary radioactive material. Some come from the sun, while many others are accelerated within the Milky Way by extreme environments such as the expanding shockwaves of supernova remnants. The origins of the rarest and most energetic examples remain uncertain, partly because charged particles are bent repeatedly by magnetic fields during their journeys, erasing the straight path that would otherwise point back toward their source. By the time one reaches Earth, it may have crossed the galaxy for thousands or millions of years while carrying almost no clear indication of where its voyage began. Yet most primary cosmic rays never reach your body directly. When one crashes into a nucleus of nitrogen or oxygen high in the atmosphere, the collision produces a rapidly expanding cascade of new particles called an air shower. Some of the fragments collide again, multiplying the shower across a region that can cover a large area of the ground. Among the short-lived particles created are pions, which can quickly decay into muons and neutrinos. Electrons, photons, neutrons, and many other secondary particles may also appear. Earth's atmosphere is therefore more than a shield standing between life and space. It behaves like an enormous natural particle detector, transforming a single incoming nucleus into a temporary family of descendants. Most are absorbed before reaching the surface, but moons are unusually penetrating. They resemble heavy versions of electrons and do not interact strongly enough with matter to be stopped immediately. At sea level, they are the most abundant charged particles arriving from cosmic ray showers, and CERN notes that roughly 1 muon per second passes through a volume the size of a human head. You cannot feel them because they usually pass through without transferring enough energy to stimulate nerves or damage a noticeable amount of tissue. Occasionally, a muon collides with atoms along its route and releases small amounts of energy through ionization, contributing to the natural background radiation that has surrounded life throughout its evolution. At ordinary ground level, this exposure is relatively modest because the atmosphere and Earth's magnetic field remove much of the incoming radiation. The dose rises at higher elevations where less atmosphere remains above you, which is why airline crews and frequent high-altitude travelers receive more cosmic radiation than people living near sea level. The muons reaching you also provide a direct demonstration of relativity. A muon at rest survives, on average, for only about 2 millionths of a second before decaying. Even traveling nearly as fast as light, a particle with such a brief lifetime should cover only a fraction of the distance from its birthplace in the upper atmosphere to the ground. Yet large numbers arrive successfully. From Earth's perspective, their internal clocks run more slowly because of their extreme speed, allowing them to survive the journey. From the muon's perspective, the atmosphere is shortened in the direction of travel. Both descriptions lead to the same result. A particle born kilometers overhead can cross your body before its existence ends. This continuous rain is not merely something scientists endure while performing other experiments. It has become a tool. Because muons can pass through thick material, but are gradually absorbed according to the amount and density of matter they cross, detectors can compare how many arrive from different directions. The resulting technique, called myography, works somewhat like an X-ray image made with naturally occurring particles instead of a manufactured beam. Researchers have used it to study the internal structure of volcanoes, search for hidden cavities, and examine large objects that would be difficult to scan by other means. A volcano does not need to be opened for its interior density to be estimated. Particles arriving from space perform the probing continuously, and instruments wait below or beside the mountain to count which ones survive. Muons are only one part of the unseen traffic. Neutrinos pass through you in vastly greater numbers. Around 100 trillion neutrinos may cross your body every second. Many produced in the sun, others created by cosmic ray collisions in the atmosphere, nuclear reactions on Earth, and violent astrophysical environments. They possess no electric charge and interact through the weak nuclear force. So almost all of them pass through your body, the ground, and even the entire planet without touching anything in a detectable way. The number sounds alarming only because human intuition treats quantity and danger as the same thing. A vast number of particles can be harmless when their probability of interaction is extraordinarily small. At very high energies, however, even neutrinos can be absorbed by Earth, and the IceCube Observatory has measured this effect using thousands of light sensors embedded deep in Antarctic ice. When a rare neutrino interacts near the detector, it creates a charged particle that travels through the ice and produces a faint cone of blue light. From that brief flash, scientists can estimate the neutrino's direction and energy, turning an almost untouchable particle into a messenger from places that ordinary light may struggle to escape. Cosmic particles also reveal themselves in simpler ways. Inside a cloud chamber, supersaturated vapor condenses around the charge paths left by passing particles, producing delicate white lines that appear suddenly and fade within seconds. A straight, narrow trail may mark a fast muon. A shorter, thicker path may belong to another kind of particle. What normally crosses the room invisibly becomes visible, not as the particle itself, but as a wound briefly drawn through the vapor. These tracks remind you that apparently empty space around your body is filled with events your senses cannot register. The room is not silent at the microscopic level. The atmosphere is producing particle showers. Unstable matter is decaying. Neutrinos are crossing the planet, and fragments of distant energetic processes are arriving without light, sound, or warning. Still, it would be wrong to describe every particle passing through you as a direct piece of a distant star. Many of the particles at ground level were born locally in the atmosphere, several generations removed from the original cosmic ray, and the enormous neutrino flow includes particles produced by the nearby sun, rather than deep space. The truth is more interesting than the exaggeration. Your body stands at the end of several overlapping particle histories. One muon may be the surviving descendant of a proton accelerated somewhere in the galaxy. One neutrino may have escaped the sun's core only minutes earlier. Another, far rarer neutrino may have traveled from a violent source beyond the Milky Way, passing through matter that would have blocked almost every other messenger. Most leave no trace, while a tiny fraction collide with an atom and briefly become part of Earth's measurable history. You normally experience your skin as the boundary separating you from the universe, but physics describes a far more open body. Matter from food and air enters slowly enough to notice, while an invisible population crosses you continuously without asking permission and without remaining. You are not being bombarded in the dramatic sense of an attack. You are standing within a natural flow that has existed longer than life itself. The atmosphere softens it, the magnetic field redirects part of it, and the structure of matter allows most particles to pass harmlessly through. Yet their presence means that the sky is never truly empty, and your body is never completely isolated. Every second, the universe sends particles through you carrying traces of stellar explosions, solar reactions, atmospheric collisions, and physical laws that only become visible when something finally stops one of them, long enough for us to notice. The black stars that never ignited, failed suns hiding between the galaxies. Some objects are born inside stellar nurseries, collapse under their own gravity, grow hot enough to glow for billions of years, and still never become stars. These are brown dwarfs, often described as failed suns, although the name can hide how unusual and active they really are. They are not black stars, dead stars, or miniature black holes, and most are not known to drift through the empty space between galaxies. They are substellar objects occupying the difficult territory between giant planets and the smallest true stars. Like stars, many brown dwarfs appear to form when cold clouds of gas and dust fragment and collapse, producing dense central objects that may initially be surrounded by disks. But the forming body stops gathering material before its core becomes hot and compressed enough to sustain the hydrogen fusion that powers ordinary stars. The dividing line is not perfectly fixed because it depends on chemical composition and other physical details. But sustained hydrogen fusion generally begins at roughly 75 to 80 times the mass of Jupiter. Brown dwarfs below that limit can briefly imitate part of a star's internal life. Those heavier than about 13 Jupiter masses may fuse deuterium, a rare heavy form of hydrogen, during their youth, and some can also destroy lithium if their interiors become hot enough. These reactions do not provide a permanent energy supply. Once the limited fuel is exhausted, the object continues cooling and fading, never settling onto the long, steady existence of a true star. A young brown dwarf may therefore glow warmly and appear more star-like than an older object with the same mass. Age becomes essential when astronomers try to identify one. A faint object could be a small young brown dwarf still radiating heat from its formation, or a much heavier and older brown dwarf that has had billions of years to cool. Unlike an ordinary star, whose sustained fusion can hold its temperature within a recognizable range for immense periods, a brown dwarf continually changes its appearance as it ages. It begins by releasing energy stored during gravitational collapse, then gradually becomes dimmer, cooler, and increasingly planet-like. This means that mass cannot always be determined from brightness alone. Astronomers must study an object's spectrum, motion, gravity, possible companion, and estimated age before deciding what it is. Even the boundary between a brown dwarf and a giant planet can become uncertain. Formation provides one useful distinction. A brown dwarf may form through the direct collapse of a gas cloud, while a planet usually forms within material orbiting a star. Nature, however, does not always preserve a clean record of that beginning, and objects of similar mass can emerge through different processes. The label describes a physical category humans are still learning to divide, not a perfectly sharp border drawn across the universe. NASA currently describes brown dwarfs as generally spanning about 13 to 80 Jupiter masses, while also acknowledging that some objects near the lower boundary may overlap with the planetary population. Although a brown dwarf may contain dozens of times Jupiter's mass, it is not dozens of times wider. Many remain approximately Jupiter-sized because adding more mass compresses the interior rather than greatly expanding the object. A human approaching one would not find a solid surface on which to stand. The visible exterior would be a deep atmosphere gradually becoming denser and hotter with depth, without a clear boundary separating sky from interior. These atmospheres can be among the most complicated weather systems known outside the solar system. Hotter brown dwarfs can contain clouds made from mineral materials that would be rock on Earth, including silicates and iron-bearing particles. As the object cools, those clouds may sink below the visible layers, while methane becomes increasingly prominent. In the coldest class, water vapor can condense into clouds, and temperatures can approach those of planets rather than stars. Astronomers organize many brown dwarfs into spectral classes known as L, T, and Y, which roughly follow this cooling sequence. L dwarfs tend to be warmer and cloudier. T dwarfs show strong methane absorption, and Y dwarfs include some of the coldest known examples. The nearby object Y's ZO855 is so cold that evidence points toward water or water ice clouds in its atmosphere, even though it formed outside our solar system and travels without shining like a star. These clouds are not motionless layers. Brown dwarfs can rotate rapidly, sometimes completing a turn in only a few hours, driving powerful winds and carrying cloudy and clearer regions across the visible hemisphere. As different atmospheric areas rotate into view, the infrared brightness can rise and fall, allowing astronomers to infer weather patterns on an object they cannot resolve as a detailed disk. Observations of the nearby brown dwarf Lumen 16A have revealed evidence of broad cloud bands resembling the organized atmospheric structures of Jupiter and Saturn, while other objects show patchy layers, dark regions, and changing brightness associated with turbulent weather. Brown dwarfs can also possess strong magnetic fields. Some produce powerful radio pulses and auroral activity, even though they may orbit no bright star capable of driving those auroras in the familiar planetary way. Researchers have detected signatures interpreted as auroras on several brown dwarfs, and Webb observations have found possible auroral emission from an isolated example, raising questions about whether internal atmospheric processes, unseen companions, or interactions with surrounding plasma provide the necessary charged particles. Their darkness, therefore, does not mean inactivity. Beneath the faint infrared glow may lie lightning-like electrical processes, magnetic storms, fast winds, layered clouds, and temperatures changing dramatically from one atmospheric depth to another. A brown dwarf is less like an extinguished lamp and more like a furnace that was never able to ignite its main fuel, slowly releasing the heat of its birth while its atmosphere transforms above it. Finding these objects is difficult precisely because human eyes are poorly suited to their light. Most brown dwarfs emit little visible radiation, especially after they have cooled, but they glow more clearly in infrared wavelengths. Surveys such as 2MASS and NASA's WISE mission transform the search by repeatedly scanning the sky in infrared light. Nearby, brown dwarfs can also reveal themselves through their motion. Distant stars appear almost fixed over a few years, while a faint object relatively close to the Sun shifts noticeably against the background as it moves through space and as Earth changes position in its orbit. Citizen scientists examining sequences of WISE images have helped identify previously unknown cold neighbors by noticing tiny moving points that automated searches had missed. Some brown dwarfs exist as companions to stars. Others orbit one another in binary systems, and many travel alone through the Milky Way. Their solitary existence does not necessarily mean they were violently expelled from a planetary system. A cloud fragment can collapse independently and produce a brown dwarf that was never gravitationally bound to a star. Some formation models also allow interactions in crowded stellar nurseries to eject low-mass developing objects, but astronomers are still determining how frequently different formation routes occur. It is possible that a small number eventually escape their birth clusters, or even their host galaxies, becoming extremely faint travelers in intergalactic space. But no vast confirmed population of brown dwarfs has been found hiding between galaxies. The phrase is more dramatic than the evidence. Most detected examples belong to the Milky Way, or to identifiable star-forming environments, and their total mass is not sufficient to explain the universe's missing matter. Their importance lies elsewhere. Brown dwarfs allow scientists to study star formation at its lowest limits, atmospheres at temperatures bridging stars and planets, magnetic activity without sustained stellar fusion, and worlds that cool continuously across cosmic time. They reveal that becoming a star is not an inevitable result of gravitational collapse. A cloud may gather, contract, heat, and approach the threshold, yet remain just below it forever. It will never illuminate a planetary system like the Sun, but it will not become truly dark either. Its fading heat may continue escaping long after the gas cloud that formed it has vanished. While mineral clouds turn to methane weather, water begins to condense, and the object grows colder with each passing age. Somewhere in the darkness, there may be brown dwarfs so old and faint that no present survey has noticed them, moving silently among the stars with atmospheres more familiar to a giant planet than to the stellar nursery where they began. They are reminders that nature contains unfinished transitions, objects that are not mistakes, but complete worlds created on the narrow boundary between two different kinds of existence, carrying the weight of stars without ever receiving their fire. The weight of invisible fields. How empty-looking space gives matter its mass. A perfectly empty box would still contain the invisible condition that helps decide why an electron is light, why the carriers of the weak force are heavy, and why matter resists being accelerated at all. This condition is the Higgs field, a field believed to extend throughout the entire universe, including regions containing no atoms, no light, and no visible objects. Calling it a field does not mean that space is filled with a hidden gas or liquid. In modern physics, a field is something that possesses a value at every location and can influence particles that interact with it. The electromagnetic field can exist across empty-looking space and produce electric or magnetic effects. The Higgs field is different because even its lowest energy state is not zero. Empty space remains permeated by a stable background value of the field, and elementary particles moving through this background can possess rest mass because of the way their own fields are coupled to it. The Higgs boson is not the field itself and does not constantly fly around attaching mass to objects. It is a short-lived ripple, or excitation, of the ever-present Higgs field, much as a wave is a temporary disturbance of water rather than the water itself. The observation of a Higgs-like particle by the ATLAS and CMS experiments at CERN in 2012 provided experimental confirmation that this field and its associated mechanism are real features of nature. The effect is often explained by comparing the Higgs field to thick syrup that slows some particles more than others, but that picture can become misleading. The field does not produce ordinary friction, and a particle moving steadily through empty space does not gradually lose speed or leave a trail of heat behind it. Mass is not a drag force. It is part of the particle's relationship with energy and motion. A massive particle can remain at rest, must receive energy to accelerate, and cannot be pushed to the speed of light. A massless particle behaves differently and must travel at light speed in a vacuum. The Higgs field changes the structure of the equations, describing certain elementary particles, so that they behave as massive rather than massless entities. Different particles interact with the field with different strengths. The top quark has a very strong relationship with it and is extremely massive, while the electron couples far more weakly and is much lighter. The photon does not acquire mass from the Higgs background, which is why electromagnetic radiation can travel across enormous distances at the universal speed limit. Gluons, the carriers of the strong interaction, also remain massless, although they are normally confined inside composite particles rather than traveling freely through ordinary space. The W and Z bosons, which carry the weak nuclear interaction, acquire large masses through the Higgs mechanism, making the weak force effective only across extremely short distances. Measurements of Higgs production and decay have continued to test the predicted connection between a particle's mass and the strength of its interaction with the Higgs field, and the results so far broadly agree with the Standard Model's expectations. The field became especially important as the early universe cooled. In the earliest hot state described by the Standard Model, the electromagnetic and weak interactions were joined within a more symmetrical electroweak system. As temperatures fell, the Higgs field settled into its present non-zero background state, breaking that symmetry and allowing the W and Z particles to become massive while leaving the photon massless. Nothing needed to switch the field on from outside. The new state emerged because it had become energetically favorable, somewhat as a material can reorganize when it cools, though the Higgs transition involved fundamental fields rather than atoms forming an ordinary substance. From then onward, electrons, quarks, and other massive elementary particles could display the properties associated with their Higgs interactions. Yet this explanation immediately opens another mystery. The theory allows scientists to describe how coupling to the field produces mass, but it does not explain why each particle has its particular coupling strength. Why should the electron interact so weakly while the top quark interacts so strongly? Why are the values spread across such an enormous range? The Standard Model accepts these strengths as measured inputs rather than deriving them from a deeper principle. Neutrinos make the problem even sharper. Experiments show that neutrinos have tiny but non-zero masses, yet the simplest form of the Standard Model does not provide a satisfactory explanation for them, suggesting that the known Higgs story may be part of a larger mechanism still hidden from view. There is also a correction that must be made whenever someone says the Higgs field gives you all your mass. The elementary quarks inside protons and neutrons do receive their individual masses through their Higgs interactions, and electrons do as well, but those contributions account for only a small fraction of the mass of ordinary matter. Most of the mass in your body comes from protons and neutrons, and most of the mass of each proton or neutron arises from the energy of the strong interaction inside it. Quarks and massless gluons are confined in an intensely active quantum system. Their motion, their fields, and the energy required to bind them together contribute to the total rest energy of the proton or neutron, and rest energy appears as mass. CERN describes roughly 99% of proton and neutron mass as arising from this strong interaction energy rather than directly from the bare, Higgs-generated masses of the quarks. The Higgs field, therefore, does not single-handedly create the weight of a person, a mountain, or a planet. Instead, it supplies essential masses to elementary particles, while the strong interaction builds most of the mass of familiar material from energy trapped inside composite particles. This division is subtle but profound. An object can be made from ingredients whose individual masses are small, yet the energetic structure binding those ingredients can make the complete object much heavier. Mass is not always a simple sum of tiny solid pieces. It can be the stored energy of relationships, motion, and confinement. The Higgs field still remains indispensable. The electron's mass helps determine the scale and behavior of atoms. Quark masses influence the differences between protons and neutrons and therefore affect nuclear stability. The great masses of the W and Z bosons shape the range and character of radioactive processes and the nuclear reactions that transform particles. Without the Higgs field in its present form, the familiar organization of matter would not merely become lighter. The balance of forces, stable particles, atomic structures, and chemistry would be radically altered. But even here, the field should not be imagined as choosing outcomes or assigning mass with intention. It is a universal physical background governed by rules that operate everywhere, from the center of a laboratory detector to the emptiest known region between galaxies. Nor should the discovery of the Higgs boson be mistaken for a complete explanation of matter. Scientists still do not know why the Higgs field settled at exactly its observed strength, why the Higgs boson has its measured mass, whether additional Higgs-like fields exist, how the mechanism connects to invisible matter, or whether it played a role in the survival of matter over antimatter. Current experiments search for small departures from standard model predictions because even a slight mismatch could reveal particles or interactions beyond the known theory. The deeper lesson is that apparent emptiness can possess physical structure without being a material substance. Remove every atom from a chamber, block every ordinary photon, and cool the chamber as far as technology permits. The Higgs field would not disappear. Its quiet background would remain woven into the properties of the particles that could enter. You experience mass as something belonging entirely to objects, as though heaviness was sealed inside each particle like material packed into a container. Physics offers a stranger picture. Some mass arises because elementary particles exist in permanent relationship with a field extending through all space, while most of the mass around you arises from energy confined within the smallest structures of matter. The solid world is therefore supported by things you cannot see twice over. An invisible field that helps elementary particles resist acceleration, and invisible internal energy that gives protons and neutrons nearly all their mass. What appears to be empty space is participating in the definition of every electron and quark within you, and what appears to be solid matter owes much of its substance not to pieces of material, but to energy held in place. Perhaps the real mystery is no longer why invisible fields have weight, but why the universe chose this particular hidden arrangement, one precise enough to turn an unseen background and confined energy into the enduring matter from which you are able to ask the question, gravity's unsolved weakness. Why the most familiar force refuses to fit into physics. A small refrigerator magnet can lift a metal clip against the gravitational pull of the entire Earth, revealing that the force shaping planets and galaxies is astonishingly weak when compared particle by particle with the other forces of nature. Gravity still dominates the large universe because it reaches across unlimited distances, acts on every form of energy, remains attractive under ordinary conditions, and cannot usually be cancelled the way positive and negative electric charges neutralize one another. A planet contains so much matter that the tiny gravitational contribution of every particle accumulates into a force strong enough to hold oceans, moons, and atmospheres in place. At the scale of atoms, however, gravity becomes almost irrelevant. Electromagnetic forces control chemistry, while the strong and weak nuclear interactions govern processes inside atomic nuclei. CERN describes gravity as the weakest of the 4 known fundamental interactions. Even though its range is unlimited, this enormous difference in strength is part of what physicists call the hierarchy problem. Nature appears to separate the scale associated with gravity from the scale of particle physics by an almost unimaginable gap, yet the known laws do not explain why that separation is so large. The mystery is not simply that gravity is weak. The deeper problem is that the theory describing gravity speaks a different conceptual language from the theories describing everything else. In quantum field theory, the electromagnetic, weak, and strong interactions are represented by quantum fields whose excitations behave as particles. Their outcomes are probabilistic, their fields fluctuate, and several possible results can contribute to a process before measurement produces a definite event. General relativity describes gravity differently. It does not treat gravity as an ordinary force transmitted across a fixed background. Matter and energy change the geometry of space-time itself, and objects follow the paths permitted by that changing geometry. This theory has survived extraordinary tests. It explains planetary motion, gravitational time dilation, the bending of light, black holes, and the gravitational waves detected from merging compact objects. But its success also makes the conflict harder to ignore. Quantum theory normally assumes that events occur within a space-time framework, while general relativity says that the framework is a physical participant whose shape responds to the events inside it. If matter can enter a quantum superposition, then its gravitational field should somehow do the same. If geometry fluctuates quantum mechanically, however, the notions of a single distance, duration, or causal order may become uncertain. Physics would then need to describe quantum events without relying on the stable stage those events normally require. A common first attempt is to treat the gravitational field like other quantum fields and describe its possible quantum excitation as a graviton. The graviton would be a massless carrier associated with gravitational interactions. But no individual graviton has ever been detected, and the gravitational waves observed by LIGO are large collective distortions described successfully by classical relativity rather than direct observations of single gravitational quanta. The mathematical difficulty appears when physicists calculate quantum processes involving gravity at increasingly high energies. In many quantum theories, calculations initially produce infinite quantities, but a limited set of measured properties can absorb those infinities through a procedure called renormalization. Straightforwardly quantized general relativity does not behave this way at arbitrarily high energy. Each higher level of calculation introduces new terms that require additional unknown information, eventually destroying the theory's ability to make predictions from a finite set of measurements. This is often summarized by saying that general relativity is perturbatively non-renormalizable. Yet this does not mean quantum gravity is meaningless, or that general relativity suddenly fails in ordinary laboratories. Treated as an effective field theory, quantum general relativity remains consistent and predictive at energies far below the scale where a deeper theory is required. It can even produce tiny quantum corrections to familiar gravitational effects, although those corrections are far too small for present experiments to measure easily. The crisis appears near the Planck scale, where gravity is expected to become as strongly quantum as the other interactions. Reaching that regime directly would require energies vastly beyond current particle accelerators, while the corresponding distances are far smaller than anything present instruments can resolve. Gravity's weakness therefore hides the very evidence needed to explain it. Electromagnetic and nuclear quantum effects can be studied in laboratories because they produce measurable changes at accessible scales. quantum gravitational effects are normally overwhelmed by stronger interactions, becoming unavoidable only in environments where immense density is compressed into an extremely small region. The interiors of black holes and the earliest conditions of the universe are leading examples. General relativity predicts singularities in such settings, regions where curvature grows without bound, and the theory can no longer provide a complete physical description. The appearance of these singularities is widely regarded not as proof that nature contains literal points of infinite density, but as a warning that classical relativity has been pushed beyond its domain and must be replaced or completed by quantum gravity. Black holes expose the conflict from another direction. Quantum theory predicts that black holes can possess temperature and emit radiation, connecting gravity, quantum fields, and thermodynamics in one phenomenon. If a black hole eventually evaporates, physicists must explain what happens to the quantum information contained in the matter that formed it. Ordinary quantum evolution preserves information, yet a simple reading of black hole evaporation appears to erase it. Proposed resolution suggests that space-time, horizons, and information are related more deeply than either general relativity or standard quantum theory reveals alone. No single explanation has yet achieved complete experimental confirmation. Several major approaches attempt to build the missing framework. String theory replaces point-like fundamental particles with tiny extended strings, whose vibration patterns include a graviton-like state, allowing gravity and quantum physics to appear within the same broad structure. It may also require additional spatial dimensions that remain hidden at accessible energies. Loop quantum gravity begins more directly with Einstein's geometric picture and attempts to quantize geometry itself, suggesting that areas and volumes may possess discrete microscopic structure rather than remaining infinitely divisible. Other programs explore whether gravity becomes mathematically well-behaved at extremely high energies, whether space-time is built from causal quantum relationships, or whether gravity is not fundamental at all but emerges collectively from information, entanglement, or microscopic degrees of freedom. These ideas are scientifically serious, but none has yet become an experimentally established successor to general relativity. Einstein Online notes that no complete theory combining quantum principles with general relativity currently exists. The weakness problem has inspired equally bold possibilities. In some models, gravity appears weak because it can spread into additional dimensions while ordinary particles remain confined to the dimensions you experience. In others, undiscovered symmetries or new particles protect the enormous gap between gravitational and particle physics scales. Collider experiments have searched for consequences of such ideas, but no accepted evidence has yet revealed extra dimensions or the new particle families expected by many proposed solutions. CERN reports that the natural solutions most often proposed for the hierarchy problem have so far received no confirming evidence. It is also possible that the question is being framed incorrectly. Gravity may not possess a conventional strength comparable to the other forces, because it may not be one more force placed beside them. If gravity is the geometry of the stage, its apparent weakness could reflect how difficult it is for ordinary amounts of energy to reshape that stage. Or space-time itself may be emergent, as fluid behavior emerges from molecules that individually possess no property called wetness. In that case, searching for the smallest piece of gravity might be like searching for a single molecule of temperature. The deeper theory would contain more fundamental ingredients, while gravity would appear only when many of them organize collectively. At present, these remain possibilities rather than conclusions. The honest answer is that physicists know with remarkable precision how gravity behaves across planets, stars, and colliding black holes, yet they do not know why its fundamental scale is so distant from the other forces, or what gravity becomes when geometry must obey quantum rules. Its weakness is therefore both a property and a disguise. It allows the ground to hold you gently rather than crushing ordinary matter under overwhelming attraction. But it also pushes quantum gravitational evidence into places almost impossible to reach. The force you encounter every moment is the one whose deepest nature remains most carefully hidden. You feel it whenever an object falls, yet beneath that simple motion lies an unresolved division in physics. The world between thoughts. What happens in the moments consciousness cannot see. Your mind can miss an event that reaches your eyes, changes activity in your brain, and influences what happens next, all while leaving you with no memory that the event was ever there. This hidden interval is not an empty hole where the brain switches off between thoughts. It is a crowded region of processing that consciousness does not fully enter, filled with sensory signals being compared, filtered, strengthened, weakened, and sometimes discarded before they become part of the experience you can describe. You normally feel as though awareness moves smoothly from one thought to another, but this continuity is partly a construction. The nervous system receives far more information than conscious attention can hold at once, so only a small selection becomes globally available for deliberate reasoning, verbal report, and lasting memory. One of the clearest demonstrations is called the attentional blink. In the laboratory, people watch a rapid stream of letters, numbers, or images and search for two important targets. When the second target appears roughly 2 to 5/10 of a second after the first, observers often fail to report it, even though the stimulus appeared directly in front of their open eyes. The first target seems to occupy a temporary bottleneck, preventing the second from gaining full access to awareness. Brain recordings show that the missed target can still trigger early sensory responses, meaning the visual system received and analyzed part of it, but later activity associated with conscious access is reduced or absent. The world did not disappear during this blink of attention. Consciousness simply failed to admit one of the events that occurred within it. A different experiment reveals that awareness can also be prevented after a stimulus has already arrived. In backward masking, an image or word is shown very briefly and is followed almost immediately by another visual pattern. The first stimulus reaches the eyes before the mask, yet the second can prevent it from becoming consciously visible. This does not mean the later image travels backward and removes the earlier one from the retina. Early processing of the first stimulus may already have begun, but conscious perception appears to require more than a single forward sweep of activity through the visual system. Signals may need to be stabilized through repeated communication between sensory regions and wider brain networks. If the mask interrupts this developing exchange, the stimulus can influence the brain without becoming a clear experience. Experiments using masking, flash suppression, and attentional blink tasks have even found neurons responding before a person reports that an image has entered awareness, suggesting that conscious recognition is the later outcome of an unfolding process rather than the instant arrival of raw sensory data. Yet it would be misleading to claim that the unconscious brain understands everything consciousness misses. Researchers still debate how deeply an unseen stimulus can be processed, partly because proving complete unawareness is extremely difficult. A person may report seeing nothing while still retaining a weak fragment of conscious information, or may perform slightly better than chance because simple features were processed without awareness. Results also depend on how visibility is suppressed and how awareness is measured. The hidden mind can detect contrasts, prepare movements, register regularities, and sometimes alter later choices. But dramatic claims that it silently performs unlimited reasoning remain unsupported. The same principle applies to thought itself. When a word suddenly appears in your inner voice, you usually do not witness the complete process that produced it. You experience the result. Before the thought becomes reportable, neural systems may already be activating associations, evaluating relevance, suppressing competing responses, and combining present input with stored knowledge. You do not consciously search every memory connected to a familiar face before recognizing it, nor do you inspect every possible sentence before speaking. Most candidates disappear before they reach the narrow level at which you can say, "This is what I am thinking." Conscious awareness may therefore resemble a limited workspace in which selected information becomes widely available, while many specialized processes continue outside it. This is one influential model of consciousness, rather than a completed explanation. And other theories place greater emphasis on recurrent sensory processing, integrated information, prediction, or the structure of subjective experience itself. Neuroscience has not yet found a single agreed boundary where unconscious activity becomes consciousness. What it has found are transitions, moments when similar sensory input can lead either to a vivid report or to no report at all, accompanied by different patterns of brain-wide activity. Some studies describe this transition as relatively sudden, with late neural activity appearing in an almost all-or-none manner when a stimulus becomes consciously accessible. Others find more gradual changes, suggesting that awareness may contain several levels rather than operating as a simple light switch. Attention may also sample parts of the world rhythmically, with performance rising and falling over brief intervals as brain activity oscillates. But there is no established universal frame rate at which consciousness turns on and off. The brain is not proven to operate like a cinema projector showing a fixed number of mental pictures each second. Different tasks reveal different rhythms, and perception can behave both continuously and periodically depending on what is being measured. Even ordinary pauses in thought are therefore difficult to interpret. When you sit quietly and experience a moment that seems mentally blank, the brain is not inactive. Sensory systems continue monitoring the environment. The body continues sending signals about breathing, balance, temperature, and heartbeat. And memory networks remain capable of producing the next association. The absence of a sentence in your inner voice is not the absence of consciousness, and the absence of a reportable experience is not necessarily the absence of neural processing. A thought may fade before the next one has taken verbal form, leaving a quiet interval that feels empty, only because no clear object occupies attention. Beneath that silence, the conditions for the next thought are already being assembled. This helps explain why an answer can arrive after you stop deliberately searching for it, why a forgotten name can suddenly return, or why your mood can shift before you identify the memory or perception that influenced it. These experiences do not prove the existence of a separate hidden thinker. They show that conscious reasoning is only one layer within a larger biological process. The world between thoughts is therefore not a secret chamber that consciousness could visit if it concentrated hard enough. It is the ongoing work that makes concentration, recognition, and thought possible in the first place. Your awareness receives selected conclusions without seeing every comparison that produced them, just as you can read a sentence without consciously calculating the shape of each letter. This hidden processing is useful because a mind forced to experience every internal operation would be overwhelmed by its own machinery. But the efficiency comes with a cost. Events can affect you without being remembered. Interpretations can form before you notice them, and the smooth story of experience can conceal how much information was rejected along the way. You feel like a continuous observer, standing at the center of mental life, yet the evidence suggests something more delicate. A moving window through which only part of the brain's activity becomes visible at any moment. Between one clear thought and the next, nothing supernatural needs to occur. The brain continues sorting the world, preparing possibilities, and deciding which small fragment will become the next thing you are able to know. And perhaps the deepest question is not what consciousness does during the moments it cannot see, but how much of the person you call you is created in those moments before awareness arrives. The observer without a body. Can information exist without anyone experiencing it? Place an automatic camera on a lifeless moon. Let it photograph a distant explosion. And then imagine that no conscious creature ever returns to examine the image. Did the photograph contain information while no one was there to experience it? Physics gives a surprisingly strong answer, but only after the word information is separated into meanings that everyday language usually mixes together. In the physical sense, information can exist as a difference, a pattern, or a correlation between one system and another. The explosion changes the arriving light. The light changes the camera sensor. The sensor changes the arrangement of electrical charges in memory, and the memory now possesses a state that depends on what happened in the sky. Nothing in this chain requires awareness. The camera does not understand the explosion. The memory chip does not know that it contains an image, and the moon does not become an observer simply because the device rests on its surface. Yet the physical record is real, because reading the memory later would allow another system to distinguish between possible past events. If the explosion had not occurred, the pattern stored in the device would have been different. Information in this technical sense is not a ghostly substance added to matter. It is found in the way physical states differ and in the reliable relationships connecting them. A footprint can carry information about an animal that has already left. A tree ring can preserve evidence of an unusually dry year, and light crossing space can carry traces of the source that emitted or scattered it. These records do not need to be witnessed at the moment they form. They only need to be physically correlated with something else. Philosophers and information theorists distinguish this pattern-based or statistical sense from semantic information, the meaning a message possesses for a system capable of interpreting it. A sequence of marks may contain an organized pattern even when no one understands the code, but calling that sequence a warning, a name, or a description introduces a different layer involving language, convention, truth, and interpretation. This distinction changes what an observer means in physics. In ordinary conversation, an observer is a conscious being looking, listening, and experiencing. In a laboratory, the word often refers more broadly to a physical system that becomes correlated with another system and preserves a detectable record. A detector can observe a particle in this operational sense. So can a photographic plate, a Geiger counter, or a surrounding environment that carries away traces of an interaction. None of these objects needs a mind. When a photon strikes a sensor and changes its state, a physical event has occurred, whether a researcher checks the display immediately, years later, or never. Quantum physics makes this issue sound more mystical than it needs to be, because textbooks frequently speak of an observer causing a measurement. This wording has encouraged the popular belief that human consciousness must force reality to choose an outcome. But standard laboratory predictions do not require a mind staring at the apparatus. What matters operationally is an interaction that links the system to a detector or environment strongly enough to leave a stable record. As quantum systems interact with their surroundings, information about certain properties can spread into surrounding photons, air molecules, instruments, and other degrees of freedom. This process, known as decoherence, suppresses observable interference between alternatives and helps explain why large objects appear to occupy robust classical states rather than visibly displaying delicate quantum combinations. Decoherence clarifies much of the transition from isolated quantum possibilities to stable records, although it does not by itself settle every interpretation of why one particular outcome is experienced. The measurement problem remains an active foundational question. Some approaches describe the environment as a witness because information about a system can be copied redundantly into many surrounding fragments. You normally learn that a table is present not by touching every atom in it, but by intercepting light that has interacted with the table. Another person can intercept different light and reach the same conclusion. In this picture, apparently objective reality becomes possible because multiple observers can access separate environmental records that agree with one another. The records exist before any particular person reads them, and their redundancy makes them difficult for one local disturbance to erase. Yet there is an important limit hidden inside this account. A physical record is not automatically an experience. The memory chip on the abandoned moon can contain a detailed image without there being anything it feels like to be that memory chip. A detector can register a collision without hearing a sound, seeing a flash, or understanding that an event occurred. Information processing and conscious awareness are therefore not interchangeable. Your nervous system also contains electrical and chemical signals, but the existence of those signals alone does not explain why some of them are accompanied by color, pain, memory, or a sense of presence. Physics can describe how a state becomes correlated with another state, how a record is copied, how reliably it can be retrieved, and how much energy is involved in storing or erasing it. It does not yet possess an accepted equation that turns a physical correlation into subjective experience. The abandoned camera thought experiment therefore contains two different questions. Does a physical pattern exist without anyone experiencing it? Yes, in the same practical sense that an unread hard drive retains distinguishable states, and a fossil preserves a structure created by an organism long gone. Does that pattern possess meaning in precisely the same way it does when a mind recognizes the explosion, understands its cause, and feels wonder or fear? That answer is less simple. Meaning may depend on a relationship between the record, an interpretive system, and a broader context. A row of electrical states can represent an image because a device architecture and decoding procedure connect those states to pixels, while the image becomes a remembered event only when a suitable mind integrates it with perception, concepts, and personal history. Without an interpreter, the correlations remain, but the experienced significance may not. This does not make information unreal. It shows that information exists in layers. At one level, there is a physical distinction, this state rather than another. At another, there is a usable signal. A system can respond differently because of that distinction. At another, there is semantic content. The signal is about something within a code or conceptual framework. And at the most intimate level, there is experience. The information becomes present to a conscious subject. Confusing these levels produces strange claims, such as the idea that the universe cannot exist unless a human observes it, or the opposite claim that a stone experiences every physical pattern passing through it. Neither conclusion follows from the evidence. Matter can carry records without consciousness, while consciousness appears to require more than the mere presence of a record. Information is also physical in another important sense. Storing and manipulating it require actual systems, and erasing a classical bit under appropriate conditions has a minimum thermodynamic cost that appears as heat released into the environment. Experiments using a microscopic 1-bit memory have confirmed the predicted link between logically irreversible erasure and energy dissipation, showing that information cannot always be treated as an abstract symbol detached from the material device carrying it. But saying that information is physical does not mean information is a new kind of matter with its own weight, or that every bit floats through space as an invisible object. It means that information must be embodied in distinguishable physical arrangements, and that changing those arrangements is constrained by the laws of nature. A carved mark, a magnetic domain, a sequence of molecules, and a pattern of light can all carry information through very different materials, because what matters is not the substance alone, but the organized alternatives it can reliably represent. This helps explain why physicists treat the fate of information as a fundamental issue, even in places where no observer can safely go. The black hole information problem arose because standard quantum theory preserves information in the evolution of an isolated system, while Hawking's original description of black hole evaporation appeared to turn detailed initial states into featureless thermal radiation, destroying the distinctions needed to reconstruct what fell inside. Proposed solutions attempt to show how information may remain encoded or eventually emerge, but the complete physical story is still debated and not experimentally settled. The argument is not mainly about whether someone watches the black hole. It concerns whether nature itself preserves the correlations distinguishing one possible history from another. If those distinctions vanished absolutely, physics would lose more than a record available to human memory. A basic rule linking past and future states would fail. The observer without a body is therefore not necessarily a hidden consciousness floating through empty space. It can be a detector, an environment, or any physical system capable of becoming correlated with another and carrying the result forward. But such an observer does not witness in the human sense. The forgotten age of the universe, when space was dark, silent, and without stars. The longest night in cosmic history was not empty. It was a construction site with every light turned off. After the universe became transparent and before the first stars began to shine, There was an extended era in which space contained no luminous objects capable of creating a true cosmic dawn. Astronomers call it the Cosmic Dark Ages, a period beginning roughly 380,000 years after the beginning of cosmic expansion and ending gradually as the earliest sources of starlight appeared hundreds of millions of years later. The name makes this age sound motionless, as though the universe paused after its fiery beginning and waited for something interesting to happen. In reality, nearly everything required for the later cosmos was being prepared during this darkness. Space was filled mostly with neutral hydrogen and helium, a small population of free electrons, faint radiation left from the earlier hot universe, and invisible matter gathering under its own gravity. There were no rocky planets because the elements needed to build them had not yet been produced in meaningful quantities. There were no familiar clouds filled with dust, no mature galaxies, and no bright objects dividing the sky into sources and shadows. If you had somehow existed there with human eyes, you would not have seen a completely black universe in the modern sense, because your surroundings would have been unlike any environment in which eyes could function. There would have been no nearby lamp, star, surface, or atmosphere to give shape to the darkness. Light existed as an increasingly cold background, but there were almost no concentrated sources producing visible scenes. The darkness was therefore not a black landscape. It was the absence of landscapes themselves. Beneath that apparent emptiness, the temperature of ordinary matter was following a subtle path. For a time, the small number of electrons left free after neutral atoms formed continued exchanging energy with the background radiation, keeping the gas thermally connected to it. Eventually, as the universe expanded and became more diffuse, those exchanges became too rare to maintain the connection. The gas then began cooling more rapidly than the background radiation because its own expansion drained energy from it. By the later Dark Ages, ordinary matter had become colder than the radiation surrounding it, producing one of the cleanest thermal environments in cosmic history. This cooling did not occur inside a perfectly smooth universe. Slight differences in density already existed, and gravity steadily enlarged them. Invisible matter gathered efficiently because it did not collide with light or experience gas pressure, forming gravitational wells into which ordinary gas attempted to fall. But the two components were not moving together as quietly as early models once assumed. After ordinary matter separated from radiation, the gas retained large-scale motions left over from the earlier age of acoustic pressure waves. In many regions, it streamed past the underlying invisible matter faster than sound could travel through the cooling gas. These coherent flows did not create a universal wind blowing in one direction. Different enormous regions possessed different relative velocities, preserving a pattern inherited from the young universe. The effect was strong enough to make it harder for small gravitational structures to capture and retain gas. Some invisible halos grew while much of the ordinary matter flowed past them, leaving them poorer in the material required to form luminous objects. This changed both the timing and geography of the future universe. The end of the Dark Ages was never destined to happen everywhere at once. Regions where the relative flow was weak could gather gas more easily, while regions with faster streaming had to wait for larger gravitational structures to develop. Simulations indicate that this effect suppressed the abundance of the earliest small-bound systems, reduced the amount of gas they could hold, and made early structure formation more uneven across space. Long before there were shining cities of stars, the universe was therefore developing neighborhoods with different futures. Some regions were becoming fertile gravitational basins, others remained delayed and almost featureless. The darkness had texture, even though it had no visible outline. The word silent is also only partly accurate. There were no living ears, no atmospheres surrounding worlds, and no stars producing the turbulent environments later found throughout galaxies. But ordinary gas could still support pressure disturbances. Matter flowed, cooled, compressed, and sometimes shocked as it entered growing structures. The universe was not silent because nothing moved. It was silent because nothing existed that could turn those movements into an experienced sound. Even chemistry had not stopped. The ingredients were extremely limited. Yet residual electrons allowed a small number of simple molecular reactions to occur. These reactions mattered because the earliest gas was trying to find ways to release energy while gravity compressed it. Still, the Dark Ages were chemically primitive compared with everything that followed. There was no carbon-based complexity, no oxygen-rich material, and no dust to shield or cool gas in the efficient ways common in later galaxies. Nature was attempting to build structure with almost the smallest chemical toolkit possible. The simplicity of this era is precisely why physicists value it. Later cosmic history became crowded with complications. Stars heated their surroundings, exploding objects scattered new elements, black holes released radiation, and growing galaxies stirred gas through countless local processes. During the Dark Ages, many of those sources did not yet exist. Matter was governed mainly by expansion, gravity, atomic physics, cooling, and the properties of whatever invisible matter shaped the first gravitational wells. This makes the era a rare theoretical laboratory. If invisible matter interacted weakly with ordinary gas, decayed, annihilated, or possessed unexpected small-scale behavior, it could have altered the temperature and growth of structure before starlight began confusing the evidence. Primordial magnetic fields or other unknown sources of energy could also have left the gas warmer or distributed differently than the simplest model predicts. Scientists cannot insert instruments into that distant age, but its hidden conditions influenced everything that emerged afterward. The masses of early structures, the places where luminous objects first appeared, and the pace at which darkness eventually gave way to light, all carried information from this unseen preparation. This is why the Dark Ages should not be imagined as a blank page between two important chapters. It was the chapter in which the page itself was being folded, stretched, cooled, and marked with invisible guides for everything that would later be written upon it. Gravity was arranging future locations without showing them. Gas was losing heat without producing visible weather. Different forms of matter were passing through one another and deciding which regions would advance first. The universe had no stars by which to announce its progress, yet it was already becoming uneven, structured, and historically irreversible. Once the first concentrated sources of light finally appeared, they did not awaken a cosmos that had been sleeping. They illuminated work that had been continuing for millions of years in complete obscurity. Every later galaxy inherited something from this forgotten interval: a distribution of matter, a supply of gas, a thermal history, and a position within a landscape shaped before brightness existed. You live in an age where the universe explains itself through light, but light is only the visible conclusion of processes that often begin in darkness. The Forgotten Age teaches that absence can be misleading. A universe without stars was not a universe without events, and a sky without visible objects was not a space without structure. It was a reality building its future where no observer could watch, reminding you that some of the most important transformations do not occur when the world becomes visible, but during the long, quiet preparation before anything has learned how to shine. The hidden geometry behind nature. Why the same shapes keep appearing everywhere. Cut open a cabbage, look down at a storm from space, examine the veins inside a leaf, or study the cracks in cooling stone, and nature begins to repeat itself in ways that seem almost intentional. Spirals, branches, hexagons, spheres, waves, and nested patterns appear in places that have never touched one another and were created by entirely different processes. It can feel as though the universe is using a small collection of hidden designs, quietly stamping the same geometry into plants, rivers, clouds, cells, and galaxies. But the truth is more interesting than the idea of a secret blueprint. Nature repeats shapes because different systems often face the same physical problems, and only a limited number of structures solve those problems efficiently. A sphere appears whenever a system tries to contain the greatest volume with the smallest possible surface. A floating droplet becomes round because surface tension pulls its outer molecules inward, reducing the area exposed to the surroundings. Small bubbles, liquid beads, and even many living cells follow this tendency. Planets and large stars also become approximately spherical, but for a different reason. Gravity pulls matter toward a common center from every direction. The similarity of shape does not mean a soap bubble and a planet are governed by the same mechanism. It means that inward forces acting evenly in all directions often lead to the same geometric result. This distinction matters throughout nature. Two objects may look alike while arriving there through completely different histories. Hexagons provide an even clearer example. Honeybees build nearly hexagonal cells because equal-sized hexagons fit together without gaps and divide a surface using relatively little wall material. The bees do not need to understand formal geometry. Repeated construction, the softness of warm wax, and the pressure of neighboring cells can help produce an efficient pattern. Hexagons also appear in the columns of cooled lava, but no biological planning is involved. As a thick lava flow cools, it contracts. Cracks spread through the solidifying rock, often meeting at angles that distribute stress efficiently. The resulting columns are frequently six-sided, although real examples also contain shapes with 5, 7, or more sides. Similar polygonal networks appear in drying mud, cooling starch, and other materials that shrink unevenly. The repeated pattern comes from stress seeking a stable route through matter. Nature is not insisting on perfect hexagons. It is moving toward arrangements that release energy and divide space with less conflict. Spirals arise from another family of constraints. A plant growing new leaves around a stem must expose each leaf to light without placing every new one directly above the last. By adding each leaf at a consistent turning angle, the plant can distribute them around the stem and reduce overlap. Sunflower seeds and pine cone scales often produce visible spiral families through this gradual process. These arrangements are frequently connected to Fibonacci numbers and the golden angle, but popular descriptions often exaggerate the precision. Not every plant follows the same numerical pattern, and nature does not calculate a mystical ratio before placing each seed. The geometry emerges from local growth rules, available space, and competition among developing structures. A spiral can also form when growth combines with rotation. Hurricanes curve because air moves toward low pressure while Earth's rotation deflects its path. Spiral galaxies develop through gravity, orbital motion, and patterns of changing density within disks of stars and gas. A seashell expands around its opening while maintaining roughly the same overall shape, producing a logarithmic-like spiral as it grows. These spirals resemble one another visually, yet each belongs to a different physical story. Their shared form reflects a common geometric truth. When something expands or moves outward while also turning, a spiral is one of the most natural paths available. Branching patterns reveal how geometry can solve the problem of transport. A tree must move water from roots to thousands of leaves. Your lungs must distribute air from one windpipe into millions of tiny exchange surfaces. Blood vessels must carry oxygen and nutrients through tissue without filling the body with one enormous channel. Rivers must drain water from wide landscapes into narrower paths. In each case, a branching network connects a large area to a limited number of sources or exits. The exact forces are different, but the challenge is similar. Reach many locations while keeping the total amount of pathway manageable. Large branches divide into smaller ones because one tube serving everything would be inefficient, while countless independent tubes would require too much material. Lightning also branches, though it is not transporting water or blood. An electrical discharge explores multiple possible routes through air, repeatedly extending where the local electric conditions favor further breakdown. Some branches stop, while one or more eventually connect and carry the strongest current. Branching can therefore emerge from growth, erosion, electrical instability, biological evolution, or fluid movement. The pattern is not proof that rivers imitate veins or that trees secretly copy lightning. It is evidence that systems searching through space often develop related solutions. Many of these networks are approximately fractal, meaning that smaller sections resemble aspects of the larger structure. A branch divides into branches, which divide again. A coastline reveals new irregularities as you look closer. A fern leaf contains smaller leaflets shaped somewhat like the complete leaf. Perfect mathematical fractals repeat forever at every scale, but physical objects cannot do this. Atoms, cells, material strength, and available energy eventually impose a lower limit. Nature produces limited fractal-like patterns because repeated local rules can operate across several levels. Not because a tree contains an infinite structure hidden inside each twig. Another recurring geometry appears when many regions grow outward at once and compete for space. The boundaries that form between them often resemble a Voronoi pattern, a surface divided according to which central point is nearest. You can see related arrangements in the cells of some plants, the skin patterns of certain animals, foams, cracked surfaces, and territories formed around competing centers. Once again, appearance alone does not establish one universal cause. In foam, bubbles press against their neighbors while trying to reduce surface area. In tissue, cells grow, divide, adhere, and deform. In a dry landscape, cracks divide material as tension builds. The same broad geometry can emerge whenever neighboring regions expand until they meet. Waves are equally widespread because disturbances often travel through connected systems. Water rises and falls. Sound compresses air. Light propagates through electromagnetic fields, and the surface of sand can organize into ripples under wind or flowing water. The materials and mechanisms differ, but repeated motion creates crests, troughs, and interference because a disturbance at one location influences what happens nearby. Symmetry also shapes the forms you recognize. Snowflakes develop six-fold structure because of the way water molecules arrange themselves in ice, yet each flake grows through a unique path of humidity and temperature, producing variation within the same underlying symmetry. Flowers may arrange petals around a center because radial symmetry allows access from several directions. Many animals develop bilateral symmetry because a body moving forward benefits from having a left and right side organized around a directional axis. Symmetry is not merely decoration. It can reduce the number of instructions required to build a form, distribute forces evenly, and help an organism or object function predictably. Yet perfect symmetry is often unstable or impractical. A developing system may begin symmetrically and then break that symmetry as small differences grow. A plant bends toward light, a crystal develops an imperfection, a flowing liquid chooses one turbulent path instead of another. The laws may permit several equivalent outcomes, but history forces the system to select one. This is why natural geometry contains both repetition and individuality. The rules constrain what can happen, while accidents, environments, and starting conditions determine which version actually appears. There is no evidence that every spiral, hexagon, and branching form is linked by a hidden mystical code. The recurrence of shapes does not prove that nature is consciously designing itself, nor does the presence of a familiar number automatically reveal a universal law. Humans are also talented pattern seekers. You notice striking similarities and often overlook the countless irregular objects that do not fit a beautiful rule. Scientific understanding begins when resemblance is followed by a harder question. What process produced this form here? Sometimes the answer is minimization of energy. Sometimes it is efficient packing, transport, growth, stress release, gravity, rotation, or competition for space. Geometry becomes hidden, not because it is secret, but because the visible shape is the final trace of forces you cannot directly see. A leaf vein records the need to move water. A basalt column records the contraction of cooling rock. A shell records years of growth around a shifting edge. A river network records how water searched for lower ground. Form is history made visible. The same shapes return because the universe has consistent laws and because matter repeatedly confronts similar limits. Space must be divided. The lost sense. Inside your body. How you know where you are without looking. Your hand can find your nose in complete darkness because your body is continuously measuring itself from the inside. Even with your eyes closed, you know whether your elbow is bent, whether your fingers are open, how much weight rests on one leg, and whether an unseen movement is carrying your arm upward or downward. This quiet ability is called proprioception, the sense of your body's position, movement, and force. It is sometimes called a sixth sense, although it is not a single organ hidden in one place. It is a distributed sensory system built into muscles, tendons, joints, skin, spinal pathways, and the brain. Vision tells you where your body appears to be, but proprioception reports where its parts are without requiring you to look. The system works so smoothly that you usually notice it only when a foot goes numb, an unfamiliar movement feels clumsy, or darkness suddenly makes balance more difficult. Deep inside, most skeletal muscles are tiny structures called muscle spindles. These are not ordinary working fibers that produce most of a muscle's force. They are specialized sensory organs arranged alongside the main muscle fibers, positioned to detect changes in muscle length. When a muscle stretches, the spindle stretches with it, and sensory nerves rapidly carry information about both the amount and speed of that change toward the spinal cord and brain. Near the points where muscles join tendons, Golgi tendon organs monitor mechanical tension and contribute information about force and load. Receptors in skin and around joints add further clues, especially when skin stretches during movement or a joint approaches the limits of its range. Proprioception is therefore not a collection of miniature angle meters attached to your skeleton. Your nervous system estimates posture by combining many changing signals produced as muscles lengthen, contract, pull, and press against the world. Muscle spindles and Golgi tendon organs are considered the principal muscular sources of this feedback, while joint and skin receptors provide additional information that becomes more or less important depending on the movement and body region. At the molecular level, much of this system depends on a remarkable protein called piezo-2. It forms mechanically sensitive channels in the membranes of certain sensory neurons. When muscle movement or pressure deforms the nerve ending, piezo-2 helps convert that physical distortion into an electrical signal the nervous system can transmit. This is the first step in turning stretched tissue into knowledge of where a limb is. The importance of the channel became especially clear through studies of people born with rare mutations that prevent piezo-2 from functioning normally. These individuals can feel temperature and pain far better than they can judge the positions of their limbs. With their eyes open, they may use vision to guide movement, but closing their eyes can make reaching, walking, and matching the positions of their arms dramatically harder. Some also develop skeletal and joint abnormalities, showing that proprioceptive feedback is important not only for movement after birth, but for the healthy development of the body itself. Once the signals leave the receptors, they do not all travel to the same destination or wait for conscious permission before affecting movement. Some enter circuits in the spinal cord, where they can adjust muscle activity through rapid reflexes. If a doctor taps the tendon below your kneecap, the brief stretch activates muscle spindles, producing a reflex contraction before you deliberately decide to move. This is not a primitive alternative to intelligent control. It is part of an efficient layered system. A walking body cannot afford to send every small disturbance through slow conscious deliberation. When your foot lands on an uneven surface, local spinal circuits and brainstem pathways can begin correcting the limb, while higher brain regions are still constructing your awareness of what happened. Other proprioceptive signals travel toward the cerebellum, which compares expected movement with incoming feedback and helps correct timing, force, posture, and coordination. Much of this processing remains outside consciousness. A separate ascending pathway reaches the somatosensory cortex, allowing you to consciously judge where a limb is positioned or how it is moving. The same sensory stream therefore serves several versions of control at once: immediate reflex adjustment, unconscious coordination, deliberate movement, and conscious body perception. Your brain also predicts the sensory consequences of movements before all the feedback has arrived. When it sends a command to lift a cup, it can generate an internal prediction of how the arm should move and how heavy the cup should feel. Incoming proprioceptive information is compared with that expectation. If the cup is unexpectedly full, the difference appears immediately in the strain of the fingers and wrist, and the nervous system adjusts grip force before the object slips. This combination of prediction and correction is why practice movement becomes fast and fluid. A pianist does not visually inspect every finger before pressing a key, and a runner does not consciously calculate every joint angle during each stride. Training refines the brain's models of how commands, forces, and sensory consequences relate. Yet proprioception is not perfectly accurate. After holding a limb in one position or strongly contracting a muscle, its sensory signals can shift, causing small errors in where you believe the joint is. Fatigue, injury, aging, neurological disease, and changes in the nervous system can also reduce precision. Athletes practice balance and movement partly because the brain can improve how it interprets and uses body feedback, not because exercise installs an entirely new sense. Studies using targeted sensoromotor training have found measurable improvements in position discrimination and movement accuracy, demonstrating that proprioception can be recalibrated through experience. The sense can also be deceived. If a researcher places a vibrator over the tendon of a stationary muscle at an appropriate frequency, muscle spindle signals may resemble those normally produced when the muscle is being stretched. A person with closed eyes can then feel a limb moving even though it remains physically still. Vibrating the tendon near the biceps, for example, can create the impression that the elbow is slowly extending. The illusion may become so convincing that the person moves the opposite arm to match a position the first arm never actually reached. This reveals that your knowledge of posture is an interpretation rather than a direct view of the body. The brain receives patterns of nerve activity and infers the most likely arrangement that produced them. When the sensory pattern is artificially altered, the inferred body can move without the physical body following it. Tendon vibration illusions have become useful research tools and are being explored as possible ways to provide movement sensations for people using prosthetic limbs or living with limb differences. Proprioception is closely connected to balance, but it is not the same as the vestibular sense. The vestibular organs in the inner ear detect head rotation, acceleration, and orientation relative to gravity. Vision supplies information about movement relative to the surrounding world, while pressure beneath the feet and proprioceptive signals from legs, hips, and neck describe the body's changing configuration. Standing upright depends on the nervous system combining all of these sources. You can feel this by standing with your feet close together and then closing your eyes. Removing vision forces the brain to rely more heavily on vestibular and proprioceptive information. Doctors use a controlled version of this principle in the Romberg test. A person who can stand relatively well while watching the environment, but becomes markedly unstable with eyes closed, may have impaired position sense pathways rather than a simple weakness of the muscles. Rare cases in which large proprioceptive nerve fibers are lost show how deeply the sense supports ordinary life. Some affected people cannot reliably tell where their arms or legs are when they cannot see them. Walking may require sustained visual attention to the feet, and turning off the lights can remove the main substitute they have learned to use. Actions that once occurred automatically must be rebuilt as conscious visual strategies. One extensively studied patient who lost much of his proprioception below the neck learned to stand, walk, gesture, and handle objects again. But movement demanded continuous attention and became far more difficult when vision was unavailable. His case demonstrates that motor commands alone are not enough. The brain must receive an ongoing report of what those commands actually caused, or it begins controlling a body whose current state it cannot reliably locate. This also explains why proprioception is central to the sense of bodily ownership. Your brain maintains a constantly updated body schema, a practical model of the sizes, positions, and possible movements of your limbs. This model is not a detailed picture permanently stored in one brain area. It is continually rebuilt from sensory input and predictions. It can even expand temporarily when you use a tool. After skillfully reaching with a grabber or cane, the nervous system may treat the tool as part of the action system, adjusting movements as though the functional reach of the arm has changed. Research suggests that proprioceptive feedback contributes to updating this estimate, helping the brain incorporate tools into the body's working geometry. Prosthetic technology reveals what happens when this feedback is absent. The physics of impossible knots. Shapes that cannot be destroyed by twisting or stretching. Tie a loop of rope into the simplest true knot. Seal its ends together, and you can pull until the cord is thin. Twist it into a new shape, flatten it against a table, or stretch it across a room, yet the knot will remain trapped inside the loop unless the rope is cut, allowed to pass through itself, or broken and rejoined. This is the world studied by knot theory, a branch of topology concerned not with the exact length, angle, or tightness of a shape, but with the properties that survive continuous deformation. In everyday life, a knot is usually tied in an open rope, so it can eventually be removed by guiding one end backward through the tangled region. In mathematics, however, the ends are joined to form a closed curve. A plain circular loop is called the unknot, while a loop containing a genuine topological entanglement belongs to a different knot type. Two loops count as the same knot if one can be smoothly reshaped into the other without cutting, gluing, or forcing one strand through another. The loop may look dramatically different during this transformation, but topology ignores those temporary distortions. It asks whether the entire history of deformation can occur while the curve remains unbroken and never intersects itself. The simplest non-trivial example is the trefoil knot, which can be drawn with 3 crossings. A left-handed trefoil and a right-handed trefoil are mirror images, and no amount of ordinary bending can convert one into the other without an illegal crossing. Much as a left glove cannot be continuously reshaped into a right glove while remaining an ordinary 3-dimensional glove. Knot diagrams make these objects appear flat by recording which strand passes over and which passes under at each crossing. But a diagram is not the knot itself. The same knot can be drawn with many unnecessary loops and crossings. So visual complexity alone cannot reveal whether 2 tangled pictures represent different structures. Mathematicians use knot invariance, properties calculated from a knot that remain unchanged under allowed deformations, to separate possibilities. Crossing number records the smallest number of crossings required to draw a knot, while more powerful tools such as the Alexander and Jones polynomials can distinguish many knots that look confusingly similar. No single familiar invariant classifies every possible knot, which is one reason the subject becomes far deeper than the act of tying rope. The geometry surrounding a knot can also carry information. Mathematicians study the space left after the curve is removed, because different knots leave differently structured complements around themselves. For a large and important class known as hyperbolic knots, that surrounding space possesses a distinctive geometry that helps identify the knot. The word impossible does not mean that these knots cannot be created. It means that once a closed loop has entered a non-trivial knot type, the knot cannot be destroyed by the permitted motions alone. This protection is global rather than local. No individual bend contains the entire knot, and cutting out one small-looking curve may not reveal where the topological obstruction lives. The knot belongs to the relationship among all parts of the loop. Tightening it can concentrate the tangle into a small region, while loosening it can spread the same structure across the whole curve. Yet the topological identity remains. Physical materials add complications that ideal mathematical curves do not possess. Real rope has thickness, friction, stiffness, and a limited ability to bend. A mathematical knot can be stretched without resistance and made arbitrarily thin. But a physical knot may jam because surfaces press against one another. Friction can preserve a knot even in an open rope, while sufficient shaking or tension may cause it to slide toward an end and disappear. Knot topology determines what is fundamentally possible, while mechanics determines whether the possible transformation can actually occur under real conditions. Experiments with knotted fibers have shown that topology and friction together can create materials capable of unusual deformation, allowing a structure to extend, rearrange, and absorb energy through the controlled movement and tightening of knots. At molecular scales, knotting becomes a biological problem. DNA is a long polymer packed into spaces far smaller than its extended length. so loops of DNA can become knotted or linked during replication, recombination, and confinement. A severely tangled DNA molecule can interfere with the movement of cellular machinery or prevent chromosomes from separating properly. Cells solve this problem using topoisomerases, enzymes that temporarily break DNA, pass another segment through the opening, and reseal the strand. The enzyme performs precisely the operation forbidden in pure topology. It changes the knot by allowing one part of the curve to cross another through a controlled cut and rejoin event. Some topoisomerases act on one strand, while others cut both strands of the DNA double helix, and failures in these systems can disrupt genome stability. Scientists can now detect individual knots in DNA using nanopores. As a DNA molecule is drawn through a tiny opening, a knotted region produces a distinctive change in the electrical signal because its compact structure passes differently from an unknotted section. Such experiments reveal that knots can slide along a molecule, tighten under tension, and change their physical behavior without changing their underlying knot type. Proteins create an even stranger case because most protein chains are open rather than closed. Strictly speaking, an open curve can always be untied by moving the knot toward one of its ends. So researchers use carefully defined closure methods to determine whether a folded protein backbone contains a deep knot-like structure. Some natural proteins genuinely fold into configurations classified as trefoil, or more complicated knots after the ends are conceptually connected far from the molecule. These structures raise a remarkable question. How does a newly manufactured chain find a folding pathway that threads one section through another without becoming trapped in the wrong arrangement? Researchers have identified knotted proteins and have even designed new proteins whose backbones adopt intended trefoil forms, confirming the final structures through crystallography. Knotting is not limited to material strings. Vortex lines in fluids, defects in liquid crystals, patterns in magnetic systems, and phase structures in quantum materials can also take knotted forms. Here, the strand may be a line around which fluid circulates or a curve defined by the orientation of a field. These knots can behave differently from ropes because the field or fluid may permit reconnection, a process in which two segments meet and exchange connections. A vortex knot that looks topologically protected can therefore untie if the underlying physics allows strands to cross and reconnect. Researchers have created and simulated knotted vortices, observing that some stretch, distort, or break apart rather than remaining permanent. More recent theoretical and experimental work has explored non-abelian vortices whose internal structure restricts reconnection more strongly. In these systems, local crossing events may be unable to reduce a complicated knot into separate simple loops, producing a more genuine form of topological protection than ordinary fluid vortices possess. This is why the phrase topologically protected must be used carefully. Protection does not mean indestructible under every possible physical event. A rope can burn, DNA can be cut, a vortex can reconnect, and a material defect can reach a boundary where it disappears. It means that within a specified set of allowed local changes, the global structure cannot be removed. To destroy it, the system must cross a forbidden barrier, break continuity, encounter an edge, or pass through a special event where its defining structure fails. That principle has become valuable in physics because local noise can distort a shape without necessarily changing its topology. A topological state may survive many small disturbances that would ruin a property stored in one precise position. But real applications require more than a beautiful knot diagram. Researchers must prove that the actual material obeys the restrictions that make the protection meaningful. The deepest lesson of knot physics is that shape can contain a kind of memory. The material may bend until none of its original curves remain, yet the entanglement preserves something about how the whole loop is connected. No single point carries that memory, and no ruler can measure it directly. It is stored across the relationship of every segment to the rest. This is why stretching cannot erase it, and twisting cannot dissolve it. The knot is not merely located in the rope. It is a property of the rope's complete arrangement in space, And when the same logic appears in molecules, proteins, fluids, and quantum defects, it suggests that nature can protect structure without making anything rigid. A form may remain soft, mobile, and continuously changing while still being unable to become ordinary. What survives is not the visible shape, but the hidden rule connecting its parts. A reminder that some structures endure, not because they resist movement, but because every permitted movement still leads back to the same inescapable knot. The final mystery of physics. Why the laws of nature exist in this form at all. Physics can predict an eclipse centuries before it happens, describe particles that no eye has ever seen, and reconstruct conditions from the earliest moments of cosmic history. Yet it still cannot answer the simplest question hiding beneath all of those achievements. Why do these particular laws exist instead of different ones? Every successful theory begins by accepting some structure. It may assume certain particles, symmetries, fields, dimensions, constants, or rules for how physical states change. Experiments then test the consequences with extraordinary precision. The Standard Model, for example, successfully describes known elementary particles and 3 fundamental interactions across a vast range of experiments. But it also contains numerical inputs that must be learned from observation rather than calculated from a deeper principle. And it leaves major phenomena outside its complete explanation. The equations can tell physicists what follows once those ingredients are supplied, but they do not yet explain why nature selected that exact collection of ingredients. Why does the electron possess its particular properties? Why are there several families of matter particles? Why do the strengths of interactions differ? Why does space have the large-scale features it does? These questions are not merely requests for more accurate measurements. They ask whether the measured facts are consequences of a deeper necessity, or whether at some level, reality simply has to be accepted as given. One possible answer is that the laws we currently call fundamental are not fundamental at all. History supports this possibility. Heat once appeared to require its own basic substance before it was understood as the collective motion of microscopic components. The rigidity, color, and sound of materials are real properties. Yet no isolated atom possesses them in the same form. They emerge when many parts interact. Modern effective field theory extends this lesson by describing laws as reliable within particular ranges of energy and distance, without claiming that the same description must remain fundamental at every scale. A low-energy observer may see one set of particles and forces, while a deeper level contains different degrees of freedom whose collective behavior produces the familiar theory. If this is correct, asking why today's laws have their form may be like asking why waves obey their familiar rules without knowing that water molecules exist beneath them. A more fundamental theory could reveal that many apparently independent facts are connected, reducing a long list of measured inputs to a smaller set of principles. This hope has guided physics repeatedly. Symmetry has been especially powerful because it restricts which interactions are possible and links phenomena that initially appear unrelated. But symmetry does not solve the final mystery by itself. A physicist can explain that a law follows from a certain symmetry, only to face a new question. Why does nature possess that symmetry, and why is it broken in this particular way? The explanation moves downward without necessarily reaching a final flaw. Even a beautifully unified theory may contain a choice of mathematical structure, state, or boundary condition that the theory itself does not determine. This reveals an important distinction between laws and initial conditions. A law describes the permitted evolution of a system, while an initial condition identifies which permitted history is actually realized. Two universes could obey the same equations and still develop differently because they begin in different states. A complete account of reality may therefore need to explain not only why the rules have their form, but why the universe occupies this particular solution among everything those rules allow. Some physicists hope that mathematical consistency will eventually leave only one possible theory. In that view, the deepest laws may exist, because every alternative contains contradictions or cannot produce a stable quantum universe. This would turn physical necessity into something close to logical necessity. Reality has this form because no other complete form is possible. No existing theory has demonstrated that conclusion. Candidate frameworks generally permit many possible states, low-energy outcomes, or ways of connecting abstract mathematics to observed physics. String theory, for example, has inspired the idea of a vast landscape of possible vacuum states that could produce different low-energy particles and constants. This landscape remains a theoretical proposal rather than an experimentally established population of universes, and even researchers who study it disagree about whether it can generate reliable predictions. If many physical environments truly exist, a different kind of explanation becomes possible. You observe laws compatible with observers because environments incompatible with complex structures contain nobody capable of measuring them. This is the basic selection effect behind anthropic reasoning. It does not necessarily claim that the universe was designed for life. It says that your location in the space of possible realities cannot be treated as a random observation independent of your ability to exist there. Yet this reasoning must be used carefully. To predict what an observer should expect, scientists would need to know which universes are genuinely possible, how often each occurs, how probabilities should be assigned, and what conditions are truly necessary for observers. Those questions remain unsettled, and studies of fine-tuning show that the consequences of varying physical parameters can be more complicated than dramatic popular statements suggest. There is also a subtle problem in asking why constants have particular values. Constants carrying units can change numerical value when humans change their system of measurement. So the physically meaningful questions concern dimensionless ratios and observable relationships rather than isolated numbers written in meters, seconds, or kilograms. Tests of whether such dimensionless relationships vary across time or space are therefore probes of whether the laws themselves have always remained the same. So far, established physics generally treats the relevant fundamental parameters as constant within observational limits, while continued experiments search for deviations that could reveal new fields or deeper dynamics. Another possibility is that laws evolve or are selected through a process resembling biological selection, with universes producing new universes under conditions that favor certain parameters. Other proposals suggest that physical law emerges from information, computation, causal relationships, or statistical regularities rather than existing as an eternal command imposed from outside. These ideas can be intellectually serious, but none has earned acceptance without distinctive evidence. A theory must do more than offer an appealing story. It must produce observations that differ from competing explanations. Otherwise, the reason offered for the laws may remain philosophy expressed in scientific vocabulary. The deepest difficulty is an infinite regress. Suppose one theory explains the known laws. What explains that deeper theory? If a meta-law selects among possible laws, why does the meta-law exist? If mathematics determines reality, why does that mathematical structure become physically realized? If every consistent universe exists, what principle defines consistency in existence? Each answer seems capable of generating another version of the original question. Physics may eventually find a framework so simple, powerful, and experimentally successful that scientists regard its structure as unavoidable. But even then, someone could still ask why unavoidable mathematical truth should produce a world that is experienced. It is possible that the question has no scientific answer because laws are the endpoint from which explanation begins. Every chain of reasoning must stop somewhere, and reality itself may be the fact that cannot be derived from anything more basic. But declaring the laws brute facts too early would risk mistaking the limit of present knowledge for the limit of possible understanding. Earlier generations also regarded many unexplained patterns as independent facts until a deeper theory connected them. The honest position is therefore suspended between confidence and humility. Physics has discovered that nature is orderly enough to be described, that the same tested relationships apply across enormous distances and times, and that abstract structures developed by human minds can predict events with remarkable accuracy. It has not discovered why the universe is mathematically intelligible, why these regularities persist, or why this particular set of possibilities became actual. Perhaps future theories will show that the laws are emergent, selected, unique, or part of a wider family. Perhaps each explanation will uncover another layer requiring its own explanation. Or perhaps the final theory will not resemble a list of commands at all, but a principle showing that laws matter observers, and possible histories arise together as different aspects of one self-consistent structure. Until such evidence appears, the final mystery remains untouched beneath every solved equation. Science can reveal the rules reality follows, but the existence of the rules themselves may be the question. Reality has not yet given us a language to answer.